tomorrow anyway, but just going over those. Diego wasn't here last week, so he may have missed some of them. Oh, and let me mark the roll. I've already marked Diego here. And Dominique, right? Okay. Hopefully the others will be coming. Okay. All right. If we got projection yet, let's go from this slide. And we've covered most of this slide before, but the reason we're starting here is that we hadn't done example 4.4, and this was a good place to do example 4.4. But before we get going on this, let me just give you a catch-up on where things are. Now, number one, I'm glad I am recording this now. In this, of course, one of my best classes of all time, Uno, research paper has been turned in so far. You are running out of weekends. If you're planning to work on it on a weekend, please get it done. There's not that many weekends left. Okay, then just a word of encouragement to people who haven't turned in. Lab 1, of the people who have or have been attending, 1, 2, 3, 4 people have not turned in lab 1, so please get those in. Test 1, 1, 2, 3, 4, okay, have not turned in test 1, have not done test 1. Lab 2, 1, I'm sorry?
Since no one's here, can I take my test 1?
A little bit louder.
I said, since nobody's here, can I take my test 1 today?
Well, I'm going to have class today, but I think we probably will finish the lab in time that you probably have time to do it then. Is that okay? You ready for it?
Yeah.
Okay. So let's try to do that. Okay, lab 2. Well, in other words, every lab, every test, there's at least a few people who haven't done it. I want to get rid of them. I want to give them back, but I can't give them back until I get them all in, or else I have to guarantee you get a 0 if you don't. So I've been holding off so everybody will have a chance to turn them in. Okay, now, so what are we going to do today? We're going to continue in chapter 4. That's heat and temperature, and I think we'll be able to get, I believe, pretty good progress made in chapter 4. We may or may not finish it. I don't know. We've had 2 hours and a half, but I've already used some of it now. We were late getting started and going over some of this other stuff. But we'll get done as much as we can, and then we'll have the second lab, the last lab, for this chapter at 3:45. And like I said, I think you'll have plenty of time after that to do the test if you're ready for it. Okay, then that means that if we do finish it today, that means the test on chapter 4 will be Tuesday. If we don't finish it today, then we'll continue and finish chapter 4 on Tuesday. Going to get started in chapter 6. We don't do 5, we do 6. And we'll get started in 6. 6 is a long chapter. It's going to have at least 3 labs. And we'll get going on 6 if we finish 4 today, we'll get started on 6 today. If not, we'll get started on Tuesday. Okay, and then whether we have time for the lab Tuesday or not, if we get enough covered, that's another issue. But hopefully we will. Okay. All right. Any questions then on what I just said? Okay. Then let's get going on this chapter. Because this is the one and only chapter, I don't know why, they have dark background with light type. I changed my pens to doing the example. So we're doing example 4.4 on page 96. Okay? Yeah. Yes. I'm sorry?
You said what page?
96. Now, that's the page that says measures of heat. Example 4, specific heat. Is what?
I said my 96 page shows example 4.4. That's what we're doing.
Yeah, that's it. That's what we're doing. Example 4.4. Okay. And here it tells us that a 1,000 kilogram car, okay, what's that a measure of? 1,000 kilograms. What's that a measure of? 1,000 kilograms. What does that measure? No, okay. Meter is a length measurement. The letter M is used for it, but that stands for, the parameter M means mass. Okay, that's the mass. If M follows a number like 1,000 M, that would be 1,000 meters. But if 1,000 kilograms is a mass unit, and the parameter for that is M. So don't get those confused, okay? They're the same letter, but used in different contexts. One has a number in front of it, meters, and one is stands for a number, that would be the parameter mass, okay? And this 1,000 kilogram car, and actually I wrote it poorly, let me go back and correct that. It's 1,000.0 kilogram car, which I find very suspicious. That means that car has a mass precisely to the nearest tenth of a kilogram, okay, which is 100 grams, which is not very much. That's the mass of the car. Yeah, right. You add a little something to it, and that's going to change. That's sort of ridiculous, okay? Is moving at 90.0 kilometers per hour. And they tell us that 90.0 kilometers per hour. Now, that's how you usually measure car speeds. However, we don't usually do that in physics class because we use meters per second. And that's the same as, they tell you this, 25.0 meters per second. Okay, thank you very much. What is that a measure of? Kilometers per hour or meters per second? What does that measure? Be equivalent to miles per hour. What do you measure when you measure in miles per hour? Okay. If you're driving here today, what did your speedometer give you things? What's that measured in? Did you drive at 60 maybe? 60 what? Miles per hour. That's a velocity or speed. Okay? So this is your velocity. Little v is velocity. Capital V would have been volume, but we're not dealing with volumes. Okay. The question is, how many kilocalories? So you're looking for kilocalories. Okay? Now, the question is, what do kilocalories measure? Now, you weren't here last time. I believe Dominique was. What do we measure in kilocalories? Okay, it's a type of energy. It's heat energy. You're absolutely right. And the symbol for heat is little q. Okay? And we'll be using that. They haven't really used it that much, but that is what we're dealing with. How many kilograms? And that's the unknown here. That's what we're looking for. That's the unknown, Q. Okay? How many kilocalories are generated when the car brakes to a stop? So initially, it's going along at a really pretty good rate. Okay, 90 kilometers per hour is not far from being 60 miles per hour. It's 25 meters per second. And you put on the brakes, and if you've ever handled anything around the brakes after someone's been driving, those brakes get hot. And the reason is, it's friction that stops the car, and the friction produces an awful lot of heat. Okay? And that's what they're asking. How many kilocalories of heat are produced when the car going 90 kilometers per hour or 25 meters per second comes to a stop? How much heat is released? Okay? So, and Dominique was absolutely right in calling that an energy, because we are dealing with energy. So if you're talking about the mass of a car and the velocity of a car, what kind of energy are we talking about with that? The what? Okay, yeah. Temperature is a measure of hotness or coldness, which is more related to heat. What I'm saying is, if what you know is a mass and a velocity, what kind of energy do you know something about? Velocity means something's moving. So the energy of, not position, but energy of motion. What is the yeah. What is the energy of motion? I just about said the word. Energy of motion is kinetic energy. Remember this? This is from the previous chapter. Kinetic energy. Does anyone remember the formula or equation for kinetic energy? And guess what? It has mass and velocity in it. Hint, hint. Anyone remember it? Kinetic energy is 1/2, ring a bell, mass times velocity squared. Okay. Have you already done the third test? I haven't gotten it graded yet, but you did do it. Okay, you have you? Okay. Huh? 1, 2, and 3. Okay. So whenever you can, let's get those done so we can move along. Okay. So let's plug in and see how much kinetic energy had to be changed to go from that speed to perfect stop. That would have been how much that friction would have happened in those brake pads and brake drums, how much heat was given off. That's what we're looking for to change that. So how much energy is that? Let's plug it up. What is that? 1/2 what? 1,000.0 kilograms times 25.0 meters per second squared. And the more that come. Okay. Here's Demetrius. Okay. Increase the class size by 50%. Okay, good deal. So I'm going to make things, I think, a little bit easier by just doing the 1/2 into 1,000, and that would be 500. Okay, kilograms. Okay. Now, 25 squared. Anyone know what that is? Believe it. Second. 625, exactly. So this will be 500 kilograms times 625 meters squared. You square the units as well as the number, okay, per second squared. Okay, multiply those two together, and I think that gives you 3,125 at least one more zero. 1, 2, 3, 4, 5. I think 2 more zeros, right? Okay, 312,500. Remember what unit this is? Joules, exactly. Kilogram meter squared per second squared is a joule. Okay. Now, if you turn back, oh, it's on the same page, I believe. Is it? Yeah. At the top of the page there, they have a conversion for you. Okay? And it's how many joules make 1 kilocalorie. You see that? Okay. So we have down here 312,500 joules. Multiply that by, I'm using my conversion factors here, I'm running out of room also, and we want this in kilocalories, because that's what it asks for here. How many kilocalories? So since the conversion gave us that, we'll use that conversion. I ask you, though, before we do, what unit do you put where? Always put the units into place. One goes on top, one goes on the bottom. Joules and kilocalories. One goes one place, one the other. Which goes where? On top and joules on the bottom. Perfect. Kilocalories on top and joules on the bottom. That way the joules will cancel out. And now we match the numbers with the units. This says that 4,184 joules, that's 4,184 joules, is 1 kilocalorie. Okay? So that means what we do, we take this number, and since this is on the bottom, divide by that number. So it's 312,500 divided by 4,184. My writing stinks, so that's 4,184. 312,500. Second. 74.7? Okay, perfect. 74.7 kilocalories. Okay. Now you might ask yourself, why when they gave you 5 significant digits here do we only have 3 here? Because this one only had 3. You can't get any more than the least precise. So 74.7 kilocalories. Okay. And you're very healthy. You're drinking water. I don't have anyone in here with a drink or any food that has, oh, are those M&Ms? Oh, could you read me oh, and by the way, a kilocalorie, when this is lowercase c, is the same as a nutritional capital C calorie. Okay? So on your, either M&Ms or crackers, I don't care which, anything, see it's the number of calories of this. 250. So you would have been able to stop a car going close to 60 miles an hour. This is a little bit of a stretch here. 250, that would be about 3 times, with the energy that's in that. Of course, you can't do it, that it's a different thing, but that's how much. Not very many, okay? That's how much heat is produced, the same amount of heat that it would take if you ran off that pack of M&Ms. You'd have to run it off. How do you phrase this? That one pack would have been enough energy to stop a car at that thing. Not that you could possess that energy, but you could have. If you had been grinding away on a treadmill, say, and that was slowly stopping the car, you could have stopped 3 of those cars with the energy that you would have gotten from that one pack of M&Ms. It's pretty amazing. 74.7 kilocalories, which is also capital C calories. Okay, enough of that. Any questions? All right, let's move on to, we already did measures of heat. Now we move to the next topic, which is specific heat. Okay? Now, this is going to be something that today's lab is going to be dealing with big time. Okay? There are some variables involved with heating. One, of course, and I think you mentioned this earlier, is the temperature change. If you're heating something up, the temperature is going to change. If you're removing heat from something, the temperature is going to drop. Okay? So one variable is temperature change. Another is mass. If you're trying to heat up a little thimble full of water as opposed to a bathtub full of water, it's going to take a lot more heat to warm up this 1 degree than it would that 1 degree. Okay? So the mass of the material. But the other thing is the type of material. Okay? Now let me give you, and I'll go and read this, different materials require different amounts of heat to produce the same temperature change. I was at a physics meeting just many years ago, and this one group had brought in, and it was pretty nifty. It was a plate, a thick metal plate, about, I'm guessing about that big around, okay? And it was metal, about that thick. And into the sides, they had drilled at least 6 or 8 holes, okay? And they had pegs that would fit snugly in those holes. But the different pegs were made out of different metals. There was a copper peg, an aluminum peg, an iron peg, probably a nickel peg. I don't remember all, but they had different. I know they didn't have any gold pegs. I noticed that. Nor silver pegs, no silver pegs, but they had the others. Zinc, perhaps. They probably had a zinc peg. But they had 6, I think it was 6 different pegs. And we were each asked to take a peg. So we did. And they took that plate and put it up on a stand, okay, and being supported by a ring there, and put a Bunsen burner under it, and cranked up the Bunsen burner. That's the thing with the blue flame, you know, in most labs they have those. And so they had that under the thing and told us to plug our pegs into the hole and hold them. Well, after a few minutes, one person let go of his. He said, "Ow," okay? And a few minutes later, another one did, and another, and another. What were we measuring? Were we measuring the wimpiness of these physics instructors? No. We were measuring the specific heat of those different metals. Aluminum had the highest, copper had of those pegs had the highest specific heat. That guy let go first, and then the aluminum guy let go, and then the iron, I don't remember the order, but everybody let go at different times because they got too hot. They heated up. Different materials require different amounts of heat to produce the same temperature change. I may have said that backwards. I probably did, okay. But anyway, the measure of that is specific heat. And this is summarized in one equation, okay? Oh, here's an example of that, and I probably did say it wrong. If we had had a gold peg, that would have been the first to release. The copper would have been next, and then the aluminum. Yeah, I got that part right anyway. I don't have the iron stuff on this thing. But aluminum, if this is 10 grams of aluminum, now, number one, this is the mass. 10 grams of aluminum, because aluminum is a very light metal. For instance, aluminum is what's used in aircraft as opposed to steel because it's lighter, okay? So if this 10 grams of aluminum went from 20 degrees to 100 degrees, that takes 176 calories to do this 10 grams of aluminum, 80 degrees Celsius, okay? The specific heat of aluminum is 0.22 calories per gram degrees Celsius. However, if you're cooling it, it would take 176 calories to be released to the environment to come from. By the way, what is 20 degrees Celsius approximately? Room temperature. It's about 68 degrees Fahrenheit, which is usually about room temperature. Whereas 100 degrees Celsius is what? From the last lab. The body temperature is around 40 degrees Celsius. 37 actually, okay? 100 degrees Celsius is the boiling point of water, way hotter than body temperature, okay? So this is going from room temperature to boiling of water. Now this is aluminum, it would boil. 10 grams, it would take 176 calories. Going that way or that way, okay? Now, if you had 10 grams of copper, number one, copper is denser than aluminum, so that's going to be a smaller box, a smaller cube, okay? And it would only take 74.4 calories to be absorbed in this. And these are little c calories, by the way, because copper has a lower specific heat. Oh, and I haven't named that yet. Yeah, measure specific heat right there. And the symbol for that is little c. Now, later in chapter 6, we're going to maybe, I think it's in chapter 6, refer to the speed of light. They use little c for that too. If you're talking about speed of light, that's the c. If If you're talking about heat and temperature, little c means specific heat. Sorry, we use the same letter for several things. Okay? But you usually don't talk about the speed of light when you talk about heat and temperature. So if you see C, you understand that. So that's a very low specific heat. So it's going to take only 74 calories. However, if you'd have had a gold peg, the gold peg would have released that really quickly, no matter how much you want to hang on to it, because it has a very low specific heat. This is less than half of copper. Copper is less than half of aluminum, but gold is less than a third of what copper is. And by the way, gold is much denser than copper too, so it's much smaller. And that probably relates to the specific heat. The atoms are being denser or closer together, and they bounce faster, and they so it doesn't take as much heat to change the same mass, even though it's different volumes, the same temperature change. Okay, just 24 calories for this one, 176. Okay, decreasing specific heat capacity is what we call it. Now here's the formula that relates all those together. There it is. Now, I put little q before. They're using capital Q here. It doesn't matter which one you use. Capital Q, that's heat. And that's usually measured in calories. Not always. Could be kilojoules or anything else. But usually it's measured in calories. In fact, here it's always in calories because you see specific heat is in calorie per gram degree Celsius. Now, if you go to a table, you'll sometimes find that also listed in kilojoules. So if it is, you'll deal with that. So this will be mass of the material, mass, times the specific heat. That's this, C. There's it for gold, copper, and aluminum. To cover others in the table. And here's the change, temperature change, delta T. In this case, it would be, delta T would be 80. Let's do this one. This is the easy one to do. That would be 80. The mass is 10 grams. That would be 800. And multiply that by 0.03. Do that quickly. 0.03 times 80. I mean 800. Sorry, 800. Okay. 0.03 times 10 times 80. 0.03 times 10 times 80 temperature. 24. See, that's where they get it. Q, that's heat, is equal to mass. There's the mass right there, 10 grams of gold, or whatever. C is specific heat of gold, and the temperature change is the final minus initial. That's 80 degrees change. Okay, we'll be using that equation in lab today, so get that equation down. Make sense? C is specific heat, measures specific heat. And that's measured in calories per gram degrees Celsius. Grams and degrees Celsius is both in the denominator. Okay? Now, before we move to heat flow, there are a couple of examples here. So let's go back and do the example 4.5. How much heat, so what is the symbol for heat? We just had it. Symbol for heat? Q, capital Q, the book uses. How much heat, that's the unknown, that's what we're looking for. How much heat must be supplied to a 500 gram pan, 500.0 gram pan. That is a very precise number, okay? Now what's that a measure of? 500 grams. What do we measure in grams? I think I asked that question earlier. What's that a measure of? I think you said meter, and I said, no, meter's a unit. What do we measure in grams? Mass, that's your mass, okay? There's your mass. To raise its temperature from 20 degrees to 100 degrees, 20.0 degrees Celsius to 100.0 degrees Celsius. What does that result in? Right, so what does that represent? A change of temperature. What symbol? Change meaning, let's go back a slide. Whoops, not that far. Go up a slide. Right there. Change of temperature. Delta T. Delta means difference. And T means capital T is temperature. Little t is time, capital T is temperature. So that's a change of temperature. So what's our change of temperature here? To go from 20 to 80, 20 to 100. How much change do you have there? 80. So 80.0 degrees Celsius is our what symbol? It's the delta T, change of temperature. Okay? I believe that's all that they had here. If the pan, one more thing, if the pan is made of iron, okay, so the symbol for iron is Fe, okay. Now, here's where we didn't do, they didn't put in the slide set, and they should have. In the book, it's on the next page, so we didn't see it yet. Now we're seeing it. Here's a table of our different materials, okay? Specific heat of selected substances. Air, just air, okay, is 0.17 calories per gram degree Celsius, okay? Or you could be using kilocalories per kilogram degree Celsius. I usually use calories per gram because you see the others just multiply by 1,000 in the numerator and 1,000 in the denominator, so they cancel out. Okay, 0.17. Aluminum was 0.22. We saw that in the previous slide, right? Concrete, 0.16. So those concrete blocks there, about 0.16 calorie of heat for every gram of block and every degree Celsius. Okay? So it's less than air, just slightly, but a lot less than aluminum. Air was less than aluminum. Copper was 0.093, remember that from before. Glass, on average, 0.160, so very similar to concrete, just a little bit less than air. I can't hold this forever. Okay. Oh, say again?
Oh, never mind.
This is on page 98. See it? Yeah. Table 4.2. Okay? Glass on average is 0.16. Gold, 0.03. We saw that in the previous slide. Ice, look at that. Would you ever guess ice has a higher specific heat than air, aluminum, concrete, copper, glass, or gold? Okay? It's 0.5. In fact, there's very few materials on the planet that have a specific heat as high as ice does. Okay? There's a couple, but we'll mention those soon. Iron, 0.1 watt. So that would have been down there between copper and concrete and glass. Okay? Lead, 0.0305, just a little bit more, very little bit more than gold. Of course, this is another very dense material. Mercury, 0.033, right in the same range. That's another very dense material. Seawater, 0.93, the biggest number so far, by almost double the next biggest, okay? Silver, 0.058. It's not quite as low as lead, but it's getting close. The soil out there, now this is on average because different soils are made up of different materials, but that's about 0.200. And steam is 0.48. Look at that. The three phases of water all have the highest specific heat of anything else on the table. 0.48 0.8 for steam, 0.50 for ice, and 1. Oh, I haven't gotten there yet. Let's do that next. 1.00 for water. The one I was thinking of was 0.93 for seawater, which is mostly water, just has a little bit of salt. Okay, so there are your various specific heats. Okay, now back to the problem. What if your material was iron? So that means we use the specific heat for iron. Okay, and what is the specific heat for iron? Have you got it on your table there? 0.11. Perfect. 0.11. It has units with it. Go up to the top of that column and you see the units are calories. These are little c calorie per gram degree Celsius. Okay? So, how much heat? That's our question. The heat, remember that formula? Anyone remember it? MC delta T. I'll scroll up to show it to you one more time. There it is. MC delta T. Okay, so back up and do our M. What's our M? 500 grams. 500.0 grams times, what's our C for iron? 0.11, and that's calories per gram degree Celsius times, and what's, we do have people here today. Thank you for coming. Okay, Zaria's here, and Michaela's here. All right. Oh! Man. It's sort of strange. I'm not used to teaching this lab on this class on a full stomach, because usually I can't get much more than my salad eaten. I didn't realize how a full meal is going to make me sleepy. Okay, but sorry. And it's also late in the week. I'm falling out. Okay, so what's our temperature? We're doing specific heat. The formula for it is MC delta T. We have a mass. This is the example 4.5 on page 97, but we get our specific heat from the table on page 98. And in this problem, what was our delta T? You had already told me? 80. 80.0 degrees Celsius. Okay, let's attend to the units first. This gram will cancel out that gram. One's in the numerator, one's in the denominator. These degrees Celsius in the denominator will cancel out that degree Celsius in the numerator, and that leaves us with heat. That's a very good thing to measure heat with. It leaves us with calories, which is, a very good thing to measure heat with. So pull out your calculators and do 500 times 0.11 times 80. Pretty good sized number. What do you get? A little louder. 4,400. 4,400, and the unit left over is calories. Now, if you find that to be too big of a number and a fairly small unit, you can go to a smaller number and a bigger unit. What would that be? 4.4 what? Kilocalorie. Perfect. 4.4 kilocalorie. Or 4.4. Now we have to here put another zero here. 4.40 kilocalories. Okay? When you go up to a bigger unit, you go to a smaller number, and between calories and kilocalories is power of 3. So move the decimal 3 places. So that was this one, 4.40 kilocalories, or 4,400 calories. On the B part here, it says, what if this were an aluminum? What was this, a pan? Yeah, a pan. What if that was an aluminum pan, not an iron pan? Now, the iron pan would be a lot like cast iron. Y'all ever cook with cast iron? Yeah, frying pan, usually a lot of times are cast iron. So it is that. Aluminum, on the other hand, and my wife has a couple of Dutch ovens that are aluminum. But if we had that, what's the specific heat for aluminum? That's little c for aluminum. It's also in the table we turned to on page 98, but it's also in the illustration on page 97. Is what? 0.22 calories per gram degree Celsius. Okay, so for this one, we'll do our Q here. I actually like to call that a delta Q because it's a change of heat, but I'll leave it the way they did. Q is equal to, what's the formula again? MC delta T. Okay, and what's the mass of the aluminum pan? 500, just the same as the other one. Now, by and large, let me just say this, 500 grams. An aluminum pan that's 500 grams is going to have the same mass, but it's going to be a bigger volume because aluminum is a lot less dense than iron is, but that's okay. Okay, 500 grams times what's the C? Say again? No, C. Specific heat. See it? See it? Yeah, that's 0.22. And that units are calories per gram degrees Celsius. And by the way, I said something wrong here. Our specific heat only has 2 digits, so we don't need that last 0. That would just be 4.4 kilocalories. That's on the last one. Come back and do this one. I just recalled there. And then what's our delta T? And there again, you said same change of temperature as before. How much? 80.0. We don't need it degrees Celsius. Okay? So, let's look at the units first. This gram cancels that gram out. This degree Celsius cancels that degree Celsius out. And that leaves us as 500 times 0.22 times 80. $8,800, is that what you got? 8,800 little c calories, which is the same as smaller number, bigger unit, 8.8 kilocalories. Okay. And by the way, that's a lot smaller amount of energy than what we had in the previous example when we were doing a big old plate. But this is that. Your package of M&M was 200 and some odd capital C calories, which is this kilocalories here. So you can rub your hands together and heat up those things very much. That's sort of a crazy way to do it, but if you rub them hard enough, long enough, you would get there very quickly. Okay. So anyway, that's your thing. So the amount of heat required to heat up an iron pan of the same mass of aluminum pan, a lot less energy to do it. That's one reason that cooking with cast iron is pretty efficient, because you don't have to heat up the metal as much, and you get to a higher temperature quicker. Okay, that was example, I've lost it. Here where it goes, example 4.5. Yeah, 4.4 kilocalories and 8.8 kilocalories. Okay. Now, let's clear this out of the way. Any questions on it before I clear it? Okay. So let's do example 4.6 on page 98. What is the specific heat of a, now this time we're doing it slightly differently. Now let me show you something here, and it's not too different from things we've done before. Okay? Here's an equation that we use when we're looking for heat. And we know the mass, we know specific heat, and we know the change of temperature. This problem we're about to read, it says, what is the specific heat? In this problem, we're looking for the C. Okay? So what you can do ahead of time if you want to, you don't have to, but it's one fairly easy way to do it, is solve this equation for C, which means we would divide both sides by m delta T. Oops, that's capital T. Divide both sides by m delta T. So the m, sorry, I hit the wrong side. The m's go out and the delta t's go out, and that leaves you C is equal to Q over m delta T. Okay? So, let's take that equation. Got to remember which way I go here. There's the equation that we're going to be using. So I'm going to erase the stuff we did over here because we lost our formula and they don't make sense hanging out there. There's the equation we're going to use now. Okay? Goodness, my nose is itching. I feel like we're going to have company. No, that's an old lunch tale. Okay, what is the specific heat? That's what we're looking for. Okay? And we know that is Q over m delta T. Okay? Of a 2 kilogram metal sample. Okay? So 2 kilograms, that's a measure of what? Anybody? Mass. That's just a measure of your mass. Okay? 2 kilogram metal sample. If 1.2 kilocalories is needed to increase the temperature. So 1.2 kilocalories, that's a measure of what? Calories measure. Not specific heat, heat. Okay? That's your Q. We're looking for specific heat. Okay? That's your Q, the amount of heat energy transferred. Okay? Is needed to increase the temperature from 20 degrees Celsius to 40 degrees Celsius. So 20.0 degrees Celsius moving to 40.0 degrees Celsius, would be what? Second? 20, and what do we call that? Delta T is equal to 20.0 degrees Celsius. Okay? So now we've got all the pieces we need. We have the 1.2 kilocalories in our numerator divided by mass, 2 kilograms, times, or divided by, also the delta 2 of 0.0 degrees Celsius. Okay? Now, you can do it either way. Frankly, I don't care for the kilos too much, so I'm going to divide both of those out. Divide by 1,000, you just got rid of the K's. Okay? So this would give you 1.2 divided by, that's calories, divided by 2 times 20, that would be 40, and that would be gram degrees Celsius, because you're multiplying those two together. So if you take the 1.2 and divide it by 40, what do you get? (1.2) divided by 40. (0.03) is your and you can either go back to kilocalories or kilograms or leave it calories. Calories per gram, goodness gracious, degrees Celsius. Okay? Now, if you wonder what material will have that as a specific heat, go to your table and see. Gold, goodness gracious. You give me 1.2, and I'm sorry. Where was it? 2 kilograms of gold. I'm golden, folks. That's my retirement. Okay, right there. 2 kilograms of gold is worth a whole lot of money. No, they're not going to give me that. Okay. It's not my going away present. They may be happy to get rid of me, but not that happy. Okay. So the answer is 0.03 kilocalories per kilogram degree Celsius or calories per gram degree Celsius. Either way, that gives you that from your table. Would be most likely gold. Now, there is a little kitchen physics applied here, concepts applied. It's easier to change the temperature of metals with a low specific heat because it doesn't take as much heat to warm them up. And of those materials that you would find in your kitchen on the table, which of those would be the best to have at the bottom of your pan? The ones listed above. Be great to have gold. I'd never cook in it, but I would go to town with it. Okay, but so gold is out. How about lead? You want to cook with a lead pan? See, that has a very low specific heat. 0.033. No, 0.0305. That's pretty low. So, y'all have many lead pans? Why not? I can think of 3 really good reasons right off the top. One, lead is really heavy, okay? Very dense material. So I don't think I'd want to be hauling around lead pans. Number 2, lead is a very soft metal. It's very dense, but it's pretty soft. And if you were scraping with a egg turner or something like that, you're going to scrape off a little bits of lead into your egg. I don't want that either. And why do I not want that? Lead is a carcinogen. In other words, it can cause cancer. And especially, say again? Yeah, you don't want lead. You don't want to cook in lead, pots and pans. Don't even try it. Now, especially with kids, besides being a carcinogen, which could do that, it also messes with developmental. It messes with the child's brain development and other development. You don't want to have lead around your kids. And that's why a few years ago, I don't know if any of you were old enough to hear it and think about it much, they were very concerned with if you go to Walmart, Toys R Us, or whatever, back when Toys R Us were open, and you buy those fairly cheap toys, where are they most likely from? Made in China. And they started checking into that, and they found out just about all of those cheap toys made in China. They were painted very pretty, bright colors with lead paint. You didn't want your kids, and kids will put everything in their mouth. You don't want them. So if you're buying toys, see if you can determine what kind of paint they're painted with. Most of them today are not allowed to be lead anyway. Some of the older toys may have that lead paint. Of course, maybe the kids have already eaten it all off. I don't know, but you don't want that to happen. So, lead is out. How about mercury? That's next. Anyone of you ever have any mercury pans? I don't think so. Why? Remember the thermometer broke in lab? That had mercury in it. Mercury's a liquid at normal temperatures and pressures. You can't cook in a liquid. You don't want to cook in a liquid because mercury is also a carcinogen. You don't want to do it. Okay, after that, silver. Oh, yeah, silver pans would be pretty good. How many of you have silver pans? I don't think so. I know we don't, okay? We barely have some silverware, so never mind. A little of that is really silver, but most of it isn't. Okay, so silver's out. What's the next one? smallest specific heat in your table. After silver, the next smallest is you see your table, page 98. We've eliminated gold. Be nice to have, but I wouldn't cook in it anyway. We've eliminated lead, carcinogen. Eliminated mercury. It's a liquid, not a solid. Wouldn't be good to cook in. Eliminated silver. Too expensive. What's the next after silver? Lowest specific heat. Anyone see it? No, I don't want a concrete pan either, but less than concrete. Right below concrete. Copper! Now, my wife does have a few, one or two pan sets that have a copper bottom and about halfway up and then stainless steel above that. That's pretty good because that copper doesn't take a lot of heat to heat that up. Those cook really fast, okay? So, yeah, copper bottom pan would be the better, okay? So, it's easier to blah, 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 okay? Harder to change the temperature of metals with high specific heats. So considering that on specific heat alone, what would you do? What would be advantages? What would be practical? We went through most of that. Okay, enough of that. Any questions on 4.5 or 4.6? So we're now ready for heat flow. Specific heat is just how much energy it takes to change the temperature of different materials. You're not talking about the flow of it. You're just talking about how much heat is required to change the temperature. Now, with heat flow, we're talking about something else. There are three mechanisms for heat transfer due to a temperature difference, okay? And these three are pretty significant here. One, and we're going to look at them individually, so I'm not going to go into great detail. Conduction, convection, and radiation. The natural flow, now get this, they've said it before, they're going to say it again, so it's pretty important. Natural flow is always, always, always from higher temperature region to the cooler one. Heat doesn't flow uphill, okay? Heat flows downhill from higher temperature to lower, cooler temperature. That's going to be true in just about everything we do in physics. It always goes from high potential energy to low potential energy. We'll run into one next chapter, chapter 6, that sort of seems like it's backwards, but there's a reason for that, okay? So let's first talk about conduction. Heat flowing through matter, okay? Let me fill in one more word here. Heat flowing through solid matter. In general, you don't talk about conduction in liquids or gases. Only in solids, okay? And here's why. The mechanism is the hotter atoms collide with colder ones, transferring some of their energy. Well, certainly that can happen with liquids and gases. But the next one we're going to look at is convection. That's what happens mostly in liquids and gases. So we're not going to mess with them now, though you can conduct in liquids and gases, but it's not nearly as much as the other. So it's usually solids where you have the atoms in fixed regular crystal patterns, and these start shaking, and that shakes these, and that shakes these, and that shakes these. That's what conduction is. Direct physical contact is required. It cannot occur in a vacuum, okay? For instance, when they heated that plate that I was talking about earlier, and we're hanging onto our pegs, that was conduction. Conducted it through the peg, okay? Now, the poor conductors are also called good insulators, okay? You have a jacket on, okay? Does it feel a little cool in here to you, or you just like having a jacket on? It's cold in here, okay. Now, what is it that makes the jacket make you feel warm? Do you know the material of the jacket? Cotton. And your shirt back there is what, Demetrius? What kind of shirt is that? Is that a flannel shirt? Probably. I think it's probably cotton. Now yours may be cotton too. Mine's probably polyester or something. But yours doesn't have the fleeciness to it. Does your jacket have a little bit of fleeciness to it? Huh? It's spongy kind of feeling. Has a little, huh?
You said a spongy kind of thing?
Yeah. Is it thick feeling or real thin feeling? Thick, exactly. Okay, what that is, it's got fleece or fabric that sort of basically holds air. See, air is a poor conductor. It is a gas, and most of the time it's going to conduct heat by ways of convection, which we haven't gotten to yet, but still air is a very lousy conductor. Okay? So, something like flannel or wool or cotton with a fleecy type feel to it, it's going to be a really good insulator because that dead airspace is going to trap, it's going to keep it from conducting the heat. Okay? What do they put in the attic of buildings? Insulation. It's an insulator. Can you describe the insulation to for me?
Like, it's soft, but it's kind of
Perfect.
mushy. So
Exactly. It has dead air trapped in it. Okay? Don't want to get into too many details here, but any of you know what thermal underwear is? Okay. Describe it for me a little bit. Don't demonstrate, just describe. Okay.
Holds heat.
It's what?
Holds heat. It holds heat.
It holds heat. And why? It's spongy. The thermal underwear has air trapped in it. Okay, just like those flannel fibers and your cotton fibers and that. Wool fibers. You know, wool has that little.
Wool doesn't.
It's what?
It doesn't keep out the air.
Okay.
It's a
If it's thin wool, but the thick wool, like a fleece jacket that has lots of spongy wool in it, that's a pretty good conductor. Now, they can weave wool into a very thin sheet, just about as thin as this, and that's not going to do any better than this would if it was cotton. Just like his shirt is probably cotton. Yours may be cotton. Can't tell what. Sorry, it is. Is that? It's cotton, but is it fleecy or is it very thin? Thin, okay, all right. So those, you see, if it's thin without those fibers to trap the air, it's not going to be a great insulator, okay? Yours is thicker and has those places to trap the air. And that's what your insulation. The old-time insulation was often called rock wool. We have a 1930s house. I think they added it later, but that was what they put in the attic, was rock wool. Not a great insulator. One of the reasons is it collapses. It settles after a while, and then you don't have as much dead air space. But more modern, they use fiberglass insulation, and that keeps its thickness pretty well, but traps lots and lots of air in between. There's a material called polyurethane foam. Boy, that's a great insulator. Styrofoam's a pretty good insulator. Have y'all seen those panels? I think they're usually pink, that sometimes they'll nail onto the outside of the building before they put the sheeting on. That's usually a styrofoam type material. Really good insulator, okay? It doesn't have to be very thick. Those are poor conductors, good insulators. The good conductors, those atoms can bind to each other, really knock into each other really quickly. The insulators don't. Here's an example. Here's a metal tube here. I'm guessing aluminum just looking at it. Doesn't matter what it is. But a tube there. You put the Bunsen burner under it. Now that's a yellow flame. Most of the time Bunsen burners are blue flames, so that's even hotter. But if you had thermometers stuck all along there, you put the flame here, soon you'll see this temperature go way up, that one goes up a little, that goes up, that maybe it's still normal temperature, but you leave this on there longer, after a while they're all up. But they go in that order. Why? Because the aluminum, the metal, is transmitting, conducting the heat down the thing. This molecule bumping into that one, bumping into that, and that, and that, and they heat up these, heat up that, heat up that, heat up that. That's conduction. The actual conduct, it's like the conductor in a train. He's the one that gets you from one place to another. That's the mechanism here too. Okay? Does that make sense? And that's generally only in solids. Okay? Generally only in solids. Liquids and gases do conduct or not conduct, but they have to be trapped so they don't move. Okay? Why? Because the next, oh wait, here we go. Here's an example. These molecules are heating up really, really quickly, right? And they're bouncing around big time, and that makes these bounce a little bit, these bounce a little less, and these a little less. Soon these are hardly bouncing at all. These are still down there. This is those people holding on to the really high specific heat thing. It takes a while for it to get down, conductors anyway, let's say that. And you'll notice that. Coming up fairly soon, I don't know if we'll do it this year or not, but my wife has gotten into, I don't mind at all, into making jams and preserves. I love those, okay? And we're almost missing the strawberry season. Well, she's been tied up with these professional meetings this week, so she hasn't done any. But we usually, when peach season gets here, we start putting up peach. So sometimes I'll stir it for her because she doesn't like to stand over a hot thing and stir it, so I'll stir it sometimes. But if I don't have the right thing, if I have a metal handled thing stirring that, after a while I can't hold it because the metal conducts the heat. So usually I use a wood stir, spoon. That doesn't conduct heat at all. If you think about it, wood has air trapped in it. Not a good conductor. Okay. So here's a sample of some conductivities. In your book, there's a table that's even more extensive. Okay, I'll put it up right here. Okay, the very best conductor of heat is silver. Look at its rate of conduction, 0.97. There it is, silver, 0.97. Just below that, copper, 0.92. They left copper off of this one. After that is aluminum. They left that off, 0.50. Then iron. Look how iron has gone down to 0.11. Okay. Lead, 0.08. They left that one off here too. Concrete, going back to this. Now this is different from specific heat. This is conduction. 4 times 10 to the minus 3. That's 0.004. Okay. Glass, 0.0025. Tile, 0.0016. Brick, 0.0015. Water, 1.3 times 10 to the minus 3. So water does conduct, but it's not a very good conductor. Okay, it's a very high specific heat. Remember, it's the highest one known to man almost. Helium's a little bit higher, but you don't find that much pure helium. So water is a very lousy conductor, which makes a pretty decent insulator. The trouble is water convects heat. We'll get to that later, just like air does. But as a conductor, if you have the water trapped, it's not going to conduct well at all. And then wood, like I mentioned, the wood handle, 0.0003 relative. That's a really good insulator. Cotton, 0.00018. Very good. That's why your cotton jacket and your flannel shirt do pretty well. Styrofoam, 0.0001. Okay, a very good insulator. Lousy conductor. Glass wool, we talked about that up in the attic. That was 0.00009. Okay, that would be glass wool. Air, way down there, 0.00006. Vacuum, absolutely zero. No conduction at all in a vacuum. Why? There aren't any atoms to bump into each other. There's nothing to conduct it, so it can't conduct it. And you see, that's why air air molecules are far apart. They're not going to bump into each other very frequently, so that makes it a really lousy conductor, a very good insulator. Styrofoam is material made of, and several other things make it poor. Water, same thing. The water molecules themselves don't conduct with each other very well. They do convect, and we'll talk about that next. Any questions? So, if you're trying to have good conductors, silver's the best. But guess what? It's awfully expensive. But just behind silver is copper. Copper is a very, very good conductor. And guess what, folks? This chapter we're talking about heat conduction. The next chapter we'll be talking about electrical conduction. You'll find they work the same way, almost exactly the same order. Okay? So let's talk about the second. This is convection. And this is energy transfer through the bulk motion of hot material. Hey, I want to add another thing here, of a hot fluid material, meaning a gas or a liquid. Okay? Solids don't convect, okay? They just can't. Liquids and gases do, and that's what a fluid is, either a liquid or a gas. The energy transfer through the bulk motion of the hot material. Now, here's what we mean by that. Okay? Excuse me. Here's what we mean by that. When you heat up air or water, then the molecules move further apart. They do in a solid too, but they're not free to move. In a liquid or gas, they are. So the ones that are further apart move up. They're less dense, and the cooler ones come in and fill in their place. That's what convection is. That movement upward of hot material. Okay? I see a lot of the people at work here, if their offices are too cool, they have space heaters under the desk. Well, the space heaters heat up the air around them, and then that hot air rises and cool air goes back and takes its place. Y'all are probably too young to remember the old schools that had radiators by the windows. You remember some of those? Okay. They didn't have anything blowing air, did they? Now, you could hear water running or steam going through those, making all sorts of noise, but they had those veins in it, and the air could move through those. And if you held your hand above that, you would feel warm air coming out the top, but you felt down near it below, and you feel cool air going underneath it. That's because of convection. Okay? The natural convection mechanism, hot air rises. Sometimes that's called the chimney effect. Hot air goes up the chimney, that's where the smoke goes to take it out of the house. Okay? You're losing a lot of heat from burning the wood, but at least you're not getting smoke in your house. Okay? Hot air rises. Hot water rises. I don't know if any of you, your moms or grandmoms, had a cookware that was called visionware. It was sort of an amber-colored glass, but the pots and pans were made out of glass, but they didn't. You seen that? Okay, if you watch that when you put it on a pot of water to boil, put it over the heat, you see after a while it start doing this. The hot water would come up the middle, that's where the eye was the hottest, and then come up, but then the part exposed to air was coolest, and then it would go back down. And you could actually see the water moving around like that, okay? And in a pot of water boiling, it usually boils in the middle first, and then later it'll be boiling all over. Hot air or hot water rises because the molecules move further apart. They are less dense, okay? And this is the old radiator. The cooler air comes underneath, goes up through the veins here, whatever you call those, and then the warm air moves up. And you just get this kind of flow. So those people sitting next to the radiator, they're going to be pretty hot. But after a while, even the people over here are going to be warming up some. All right. Brandon is good. All right. Now, I did have one other example back on conduction. Any of you used to like watching high school football? Yeah, okay. Especially those late in the season games, maybe the playoffs and stuff, when it's already getting really cold out there. And maybe you go to you're the visiting team, you go to the other, or even your home stadium, and they had either nice, new-looking aluminum bleachers here or the older wood bleachers down there. Which do you want to sit in on those cold nights? Why? Those are older. They're splintery. Why do you want to sit there? They're what? Okay. Guess what? Those bleachers have been out there in that cold temperature, both of them the same temperature, everything. They're at the same temperature. They really are. But the aluminum feel colder, don't they? Here's why. Aluminum's a metal, is a good conductor. You sit your tush down on that, and your tush that was about 90 degrees or so, the aluminum starts pulling it out and trying to warm up the whole bleacher there because it's a great conductor. So it feels like it's 40 degrees out, 45, whatever the actual temperature is. But you sit on the wooden bleacher, and it's a lousy conductor, so it soon comes right up to your temperature, maybe 85 or something like that, but it feels a lot warmer. That's because the metal is a good conductor, the aluminum, the wood is a good insulator. Okay? Make sense? Okay. Well, that's back on conduction. This is convection. Hot air rises. Okay? Especially air or liquids. Now, here's what's going on with that, and this is, to me, a fairly lame example, but it's true. If you had two volumes of air, same number of molecules, same number of everything, they're exactly balanced. And you heat this one up, moving the molecules further apart, but you let the container grow too, and it's still going to have the same mass, okay? And it'll be balanced. But then if you just took a little segment of that, like this was, and put them here, all of a sudden it's going up because this one's heavier, denser, and this one's lighter. It's going to rise, and the denser air falls. Okay? So that's what's happening with convection. Okay? Both liquids and gases, which are both classified as fluids, they convect. They don't conduct. And that's why it's hard to use water as a insulator, because it's convecting, not conducting, but it's convecting pretty efficiently. Okay? Air, if you can keep it still, like trapped in the fibers of your jacket or shirt or whatever, then it is a pretty good insulator. But if you allow the air to move, the hot air is just going to leave your body as soon as it can. All right, the third type of energy transfer or energy flow is that of radiation. Okay? Now, I don't know if you can feel it where you are. You're probably blocked by that thing. But if I were to put a little thermocouple here on the desk here, right here, or even my hand, and move it over here, which I can feel warmer or cooler. Yeah, that's the warmer. I can feel a difference there. Here it feels cool. Why? Because the radiation that's coming through the glass, through the air, through everything else, that's transmitting heat. That's called infrared radiation. Whereas where the shadow is, that's cooler. Okay? Radiation is radiant energy is the energy associated with electromagnetic waves, light waves, gamma rays, infrared rays, any kind of electromagnetic waves. Now, not only can they operate through a vacuum, they operate most efficiently through a vacuum. They do not need a medium to transfer through. Whereas a conduction has to be in contact, so mostly solids. Convection has to have molecules to expand and contract, so it's mostly liquids and gases, okay? But radiation, it'll go through glass, it'll go through air, it'll go through water, but it's most efficient through a vacuum. It doesn't need material. this electromagnetic energy going through the space. Now, here they just sort of jump into something else. All objects emit and absorb radiation. Okay? If you feel this desk here, I put my hand down into the light and shadow, I can feel the radiation hitting my hand. But you feel the desk that's warmer there than it is there, because that's been there. So all objects emit and absorb radiation. Even that fake wood desktop, okay? That absorbs the radiation coming in through the light, and then when you put your hand on it, it's emitting and warming up your hand, okay? Now, the temperature that you feel there determines I think I have this backwards. The emission rate, I think, determines the temperature, but you understand what they're trying to say. The temperature determines the emission rate. In other words, the hotter it is outside, the hotter it's going to feel on that desk, okay? So the temperature determines the emission rate, the intensity of the emitted light, okay? Now they're talking about the stars out there, or maybe an incandescent light bulb. The higher the temperature, the more the intensity of the light coming off, and the type of radiation given off. Now our sun is giving off, enormous amounts of radiation. Of course, very little of that reaches the Earth, okay? And that little bit that reaches the Earth is high intensity, but thank goodness we have a part of our atmosphere called the ionosphere, and that blocks most of that harmful radiation from ever getting through. So therefore, we are safe down here. We don't get fried by that high energy radiation. Only light, that little narrow band between violet and red. Violet, I have to do the other thing. Red, orange, yellow, green, blue, indigo, and violet. Okay, Roy G. Biv. Okay, going the other way I can do it, but it takes me a lot longer. Those are what the atmosphere allows through. A little bit of ultraviolet comes through, and that's why we get skin cancers and wrinkled skin and spots on our faces and things like that. Sunburns, those kinds of things. That's why we get cataracts, other things like that. We talked about that before, okay? But mostly the atmosphere blocks most of that from coming across. However, the atmosphere traps infrared radiation, which is heat, because the amount of heat of energy coming from the sun getting blocked by our atmosphere, the Earth would be way too cold for life, except that the atmosphere traps the heat, okay, the infrared radiation. That's called the greenhouse effect. It's necessary. Too much carbon dioxide in the atmosphere makes it happen more than necessary, and it may give us some pretty serious problems. Okay, the temperature determined by the balance between the rates of emission and the rates of absorption. The Earth typically absorbs and emits just about the same thing. However, when it absorbs more than it emits back, we can have global warming. That's the problem. Now, when I drove into work this morning, they were saying there was a chance of rain this afternoon. Okay, now this morning it was in the, I think it was upper 60s, lower 60s. So I didn't have my windows down. So when I parked the vehicle, I knew I was going to turn around and drive back to the Birmingham campus at 10 o'clock. I rolled down my windows and cracked. Now, why did I do that? Now, this afternoon, when I came back around 11:45 or whatever time it was, I decided to roll my windows up. Just because the wind was blowing like it's been blowing now, I was afraid it was going to blow up with a thunderstorm. I didn't want a wet seat when I drove home, so I closed my windows. But if we continue like this all afternoon, now it's probably going to be 6 o'clock before I leave, so it's not going to be all that warm anyway. But if I were to go out there and get in the vehicle now, since I rolled the window up, what would I find when I open the door? It's going to be hot, because the glass allows the light in, but when it comes in, that light, which was infrared, which was light spectrum radiation, comes through the glass, it warms it, it slows down, not slows down, lengthens the wavelength, decreases the frequency, which makes it infrared radiation. So it's what they call the greenhouse effect. The glass in the windows of my vehicle is going to make it get hotter inside than it is outside, just like a greenhouse does. Okay? So that's what our atmosphere is doing. When you have extra carbon dioxide in the atmosphere, it's an even better greenhouse. Okay? And so right now we are absorbing radiation a little bit faster than we're re-emitting it. So we're very slowly getting warmer and warmer. Now, it's not constant, it's not consistent, but generally we're getting warmer. I think I can remember hearing that we've set, on the average, record highs something like the majority of years in the last decade. Maybe 8, 9 of those 10 years were record high average temperatures every year. Hey, that's warming up, folks. Now, some people say, but it's not because of what man's done. Hey, who's been burning fossil fuels like crazy, putting more carbon dioxide in the atmosphere? We are, okay? Oh, but it's not enough to make a difference. Look at the difference, okay? What else could, oh, it's just a natural cycle. I don't think so. Natural cycles don't happen this rapidly. Okay, never mind. That's a big argument today. All right, so we talked about each of those. Conduction, mostly solids. Convection, mostly fluids, liquids and gases, and radiation. All right, there's a few blurbs here. Science sketch. I'll let you read that one. That's pretty lame, I think. How convection works, that's probably a little bit better. So I would definitely read these. So we're now down at 4.4. Energy, heat, and molecular theory. Okay? That's what this one is. Okay? Now, if I'm heating up a material there, right now the light coming in is heating up the desktop. Okay, that's all. But if I put a pan of water there, it could be heating the water, but sometimes that water actually feels not really as hot as it was before. And well, how do you reckon so? What else? If I left that pan there long enough and the sun shone in there long enough, what would happen to the water? It would evaporate away. Okay? So here's two things that happen. Two responses of matter to heat. One is the temperature increases within a given phase. So if that was water there and you weren't allowing it to evaporate, it's going to change temperature. It's going to be water at a higher temperature within a given phase. The heat goes mostly into internal kinetic energy. The molecules bounce into each other faster, harder, bounce away. There you're dealing with specific heat. So you would have to look at that. Desktop, what's its specific heat? The water, what's its specific heat? You would determine the heat transfer that way. Okay? However, oh, and here's how they describe this. Now this actually is going a little bit further, so we'll hang on to this concept for the next thing too. But let's say we started with ice. Now, have you ever gone to the freezer to pull out some ice? Probably Mama didn't want you to do it with your hands, but you did anyway. And got out a cube of ice. Did it immediately melt in your hand? No. It stayed solid. In fact, if your hands were slightly wet, what did it do to your fingers? It froze the water on your finger, and now you had it stuck to your hand, and it was hard to get off, right? Have you ever had that happen? That's what happened. You didn't melt it, so you were just having to increase the temperature of the ice so you could get it to a point where it would melt, okay? Now, the ice we did in the lab last time, it was right at the melting point, because when I pulled it out of the fridge, there was a little bit of water in there where it started melting, but the fridge was pretty cool, so I had to add some water to it to get it so it would, you could measure it with your thermometers, okay? So, here you've got solid matter and that's conducting. If it's conducting at all, that's what it's doing because it's solid. Once you get it into the liquid phase, then they're bouncing around like this. So you change the temperature here, they just bounce more. Change the temperature here, they move more. Change the temperature once it's a gas, water vapor, steam, then they just move faster. Okay. But the second thing we're going to get to is how do you go from solid to liquid and liquid to gas? That also requires energy, but those places you don't have any temperature change. Here you have temperature change moving from moving slowly to moving faster, moving faster. At some point it starts melting. Once it starts melting, no temperature change. Remember that in lab? The ice was melting in the containers which you read, and as long as there was ice there, it was always at 0 degrees or something pretty close to it. Remember that in lab last time? So while the ice was melting, you had no temperature change. Okay? Now, as we'll see today, when the ice stops melting, we'll see that in another way. Okay. So anyway, this is the first thing. If you heat matter, you could increase the temperature. That depends on specific heat. That's the internal kinetic energy, how fast the molecules are moving. Whether they're bound in a solid crystal structure, free to move around in the liquid, they're moving faster, or in gases, they're even moving faster. Okay. Now, the second thing that happens is you can have a phase change. If you had the ice cube and you held it long enough, it would soon finally quit sticking to your fingers and it would start melting, right? Because your body heat would do that for you. Your hand would get awfully cold before you did that, but it would happen, okay? That is called the phase change, going from a solid ice to liquid water. Or you get it hotter and hotter and hotter, and you have that water like we did in lab, bring it to a boil, now it's going into water vapor. There you have the temperature change. And when you measured the temperature of the boiling water, did it go up even though the water was still boiling? No, it was right around 100 degrees Celsius. Because at the phase change, your temperature doesn't change. Okay? So the phase change at constant temperature, that's related to changes in the internal potential energy, and you're increasing that internal potential energy, but not changing kinetic energy. Temperature depends on kinetic energy. So that's called latent heat. Now this word latent actually comes from the Latin word, I think it is, meaning hidden. Hidden heat. You're adding heat to it, but you don't see a change in temperature. Okay? That's called latent heat. Now there's a couple formulas for this. We already have the one for specific heat. Remind me what that one is. Q is equal to MC delta T. Perfect. Okay? Now let's do the latent heat one. They give it in the book. They don't give it on the slide. I don't know. I don't think they do. Let me look and see. No, they don't. Okay? Here's the latent heat one. There are actually two latent heats we've talked about. One's the latent heat of melting, or if you're going the other direction, freezing. Now, both of those are called the same thing, the latent heat of fusion. Sounds like freezing, but they use that for freezing or melting. So here's one. The latent heat of fusion. And this could be melting or freezing. Okay, either one, melting or freezing, that latent heat of fusion. Okay, now it looks a little close to the other. It's, I want to say lambda, but I can't remember if that's the one this book uses. No. Okay, no. It's the mass. Mass was involved with the other two, remember. Oh, this is what threw me off. Okay. Let me go back. I'm using the symbol where I need to be. Okay. Latent heat of fusion is L sub F. Okay. And that's measured in calories, just like specific heat was, per gram. no delta T. Okay, remember, let's go back to this one. This is mass is measured in kilograms or grams. Let me just put grams, that'll make it easier. Okay, that's ugly the way I've done it. I erased too much. Mass in grams. Okay, what was specific heat unit? Do you remember that? Specific heat. We did several problems with it. Remember what it was? It's the units for specific heat. Anybody? Units for specific heat. Anybody? Nobody? It's calories per gram degree Celsius. Remember that? Because here grams canceled that grams, the delta T, that's measured in degrees Celsius. So they canceled out. And that left you Q in calories. Okay? Now, let's do it for specific heat. It's calories per gram, but you don't have a delta T. Why? Constant temperature. There is no change of temperature with latent heat. So rather than calories per gram degree Celsius, it's just calories per gram. Okay? So here then is our formula. The Q, that the heat transfer, is equal L sub F, if it's melting or freezing, times mass. M times L sub F. Mass times the latent heat of fusion. There is no delta T. There's no change of temperature. Don't put it in there. But there's another kind of latent heat, and this is called the latent heat of vaporization, L sub V. Okay? That's also in calories per gram, same deal, but it's just a different number. This is the latent heat of evaporation or condensation. Okay? Now, can I ask you a question? Brenda, was that drink cold when you first got it?
Mm-hmm.
Is it still pretty cold? Touch the outside. Is it damp? Yeah, why? Did it leak through that container? Why not? What is the dampness that you feel on that? Okay, condensation. Water vapor that's in the air right here, because that was significantly below the temperature of the region, then that some of that water vapor in the air condenses on the bottle. Okay, I was going to ask you that, but I was afraid yours had been sitting in here too long, and it probably wouldn't have any condensation on it. But yours just brought it down. Okay, so yeah, that happens, especially down here in the South in the heat of summertime. When we talk about, man, how humid it is outside, you get a glass of ice water or a Coke can or something like that, you've just gotten out of the fridge, set it down, immediately you get water molecules on it, right? Water droplets on it. I was doing, when I worked at Southern Research Institute, we were working on a radon project, and we had some experts from way up in northern New York State, way up there near the Canadian border. And they came down to a meeting we were having in Orlando, Florida. And he would pour himself some ice water, and immediately the outside of the glass was just dripping with water. He said, "How can that happen so fast?" I said, "You're in the humid South here." Okay. Up north, it was never that humid. It took a long time for those little droplets to form. And they probably didn't drink that much ice water anyway because it was already so cold up there. But boy, down there, it just immediately, he said it's remarkable how fast that happened. And it is, okay? So that's the latent heat of evaporation or condensation. And you're absolutely right, that's condensing. And the same formulas, the Q, the heat gained or lost, is equal to the mass times that latent heat of vaporization. Okay. Now, the specific heat was specific for every certain material. We saw the table of it. Same thing with latent heats, but they're different for fusion and vaporization of even the same material. Okay? So let me get that information to you. It's in a table here in your text. I've just got to find the table. Ah, there it is, on page 104, table 4.4. But before we go there, they have a couple, and they have the same illustration twice, but it's a really good one, so hang on to it. Now, what have I done with my watch? I was pretty sure I brought it down here, but I don't see it. No. Don't tell me I've lost my watch today. Maybe I left it in my office. Yeah. I hope not. That was a Christmas present from my wife, so I'll be in deep trouble if I lose that. The pin broke on it, and I've been carrying it around rather than wearing it. And I don't know where that's going to now. Yeah, I thought I had it in here. Okay. It must be down. I hope it's down in the office. Okay. So here is the figure, and this is a really good figure. It may not be particularly easy to follow at first, but it is a really good figure. Okay, it shows several things here. Here is your temperature, okay? And it shows it going from minus 20 degrees Celsius to something way over 100 degrees Celsius, maybe even 200 degrees Celsius, okay? Now, here is the amount of heat you're inputting. In other words, it's gaining heat going this way. It would be losing heat coming this way. Now, later we'll see this again, I think. No, we won't, okay? In the book, you'll see it twice. Here, you only see it once, okay? In the book, well, it says the same thing. It's almost, yeah. I'll try to combine the two, okay? Neither one of them say when you're removing heat, the heat is going this way. You could imagine that. And that's calories. Increased calories going this way, increased temperature going this way. Now, as long as you're below 0 degrees Celsius, that ice is cold, okay? Really, really cold. You add heat to it, it just gets to be a little bit warmer ice. It doesn't melt the ice until you get it to 0 degrees. So you can have, and if you go to your freezer and open your freezer and pull out a piece of ice, a cube of ice, you will find it doesn't immediately melt. It may actually, like we said before, freeze your, if you got moisture on your skin, freeze it to the cube of ice. Now, do y'all remember the movie, I think it was named A Christmas Story? Okay, is that the one where the kid, some kids told him to put his tongue on the flagpole? It was very, very, very cold, like Minnesota or somewhere like that, and then it got stuck to the flagpole because the moisture on his tongue froze to the flagpole. Not a good thing, right? Now that was Hollywood, but I'm sure that's happened before. In fact, I'm absolutely certain because my wife's brother is 4 years younger than she was, so she was witnesses, but then their sister is 2 years younger than Keith. Now Keith is Mr. Gentleman Quarterly. I mean, he's tall, dark, handsome, dresses immaculately. I mean, he's a good-looking guy, and he dresses like a good-looking guy. You know, he makes good money. He's Mr. Cool. But when he was younger, he wasn't quite. He was always a nice guy, but he could do some really dumb things sometimes. And one time, his mom had him and Carrie, that's the younger sister, in the store. I'm guessing Carrie was maybe 3 or 4 years old. She could walk around. She understand things. And Keith was only 2 years older than her, so he was 6 or 7. And the mom was rushing around the grocery store trying to get what she needed, and she hadn't paid attention to where the kids were going out there. It was a hot summer day too. And so she was almost through and said, Terry, go get Keith. Where's Keith? You know, and so Terry went back looking for him, and she came back and said, Mom, you need to come get Keith. She said, well, why didn't you bring him? He said, well, he was there by the frozen foods or whatever. I don't know what she said. And she said, well, why didn't you tell him to come? And she said, well, I did. But he said, okay. And she said, so I went to get you. So she went back there, and Keith saw the ice forming in the frozen foods and thought, oh, it's so hot here, that would feel so good to lick the ice. So he bent over the ice and licked it and got his tongue stuck to the frozen ice on the freezer compartment. And poor Mrs. Brazil, she was horrified that her son would put his mouth down next to where people were buying food. So she just grabbed him by the collar of the shirt and yanked. And of course he started bleeding, his tongue started bleeding, and she was even more embarrassed. So she just rushed him out of the store, put something over his mouth while he was screaming, rushed him out of the store, and took care of him at home. That was real life story. We love to tell his kids that, you know. He can't stand it. Okay, but anyway, Mr. GQ. Okay, but anyway, that ice, when you're at very low temperature, minus 20, that's not going to melt. You add heat to it, it just warms the ice. It warms the ice. What is the formula that warms that ice? Does anyone remember? Now this, I think I will go back to black, or dark anyway. The formula when you're warming something, when you're changing temperature, that heat being transferred is, anyone remember the formula? MC delta T. Because you have a change of temperature, you're talking about specific heat. Remember, specific heat for ice was 0.5 calories per gram degree Celsius. Okay? So whatever the mass was times your specific heat of ice times the change of temperature. That's to warm the ice. That's all you're doing. You're not melting the ice. But when you do finally reach it up to 0 degrees, and you warm the ice to 0 degrees, if you continue adding heat, it's going to melt the ice. But when you're melting the ice, you're not changing the temperature of the ice. So when you're changing temperature of the ice, you're not melting it. When you're melting it, you're not changing its temperature. It stays the same. So what formula would we use there? There's a phase change. What would that formula be? It's also a Q, but what would the formula be? M times L sub F, latent heat of fusion. Perfect, okay? Now, when you get all that ice, and this is what we did in lab last time, as long as you had water and ice in conjunction with each other, you stayed at 0 degrees or awfully close to it, okay? But then when finally all the ice melted, and we didn't let it get that far, but if we had, then finally, and only then, would the water start warming up. What formula do you use here? Change the temperature of the water. Anytime you're changing temperature, it's the same formula. Q is equal to MC delta T. The difference here and here is specific heat of ice is 0.5, specific heat of water is 1. The highest specific heat of any substance, just about any substance on the planet. Helium is a little bit higher, but how much time do you have lots of grams of helium gas? You don't, okay? Helium does have a higher specific heat. Water has just about the highest specific heat. Now, can anyone think of some ramifications of that? The fact that water has such a high specific heat. Do you use water in your car anywhere? Where? Anybody? Do you ever put water in your car? The what? There is a thing up front that looks like a tank. It's called the same thing. The thing by the window was called in the schoolroom a radiator. But the thing is, where the one in the schoolroom is adding heat to the room, the radiator in your car is taking heat away. Because you see, water has a very, very, very high specific heat, so it removes that heat that's going on. When you're doing internal combustion in your car engine, that means you're burning fuel, okay? And if you're burning fuel, you're producing a lot of heat. Now, some of that energy goes to pushing the piston up and down, that kind of stuff. Yeah, that's what turns the car. But a lot of that heat is wasted. And if you didn't have a way to get that heat away from there, you're going to warp your engine, okay? So you have water in your radiator that's always circulating through the engine block, taking the heat away. And they use water because it's the highest specific heat of any substance, commonly occurring substance on the planet. Now, we can't use pure water. Does anyone know why? There's actually two reasons, but anyone know why we don't use pure water in our radiator? We use something else. Anyone know? When you take it to the shop, they usually take care of it for you. Hint, it's necessary in the wintertime. Talked about this. Say again? Yeah, so your water won't freeze when it gets below 32 degrees. And it does. Even here in the South, it gets below 32 degrees occasionally. Not often and not for long, but it will. And if you didn't have something in the water to lower the freezing point, you're going to burst your pipes. And you could crack your head. You could do all sorts of bad things if you didn't have it. And what they put in there is called antifreeze, because it keeps the water from freezing. Okay? Well, then you might say, well, why wouldn't you use pure antifreeze? Why do you have any water at all? Because antifreeze doesn't have as high a specific heat as water. You need the water to conduct the heat away, or to take the heat away, but you can't use pure water because of antifreeze. Now, the other thing that antifreeze does for you, a beneficial thing, is just sort of a side issue. Water will rust metal like crazy. You know, anything that's iron. Especially hot water is especially bad. Well, the antifreeze also has something in it that retards rusting. So that's the second thing it does for you. Retards the rusting. Okay. Okay. Now, so here you're heating the water. You heat the water. You heat the water. Here you use specific heat of water, but you use the C of water rather than a C for ice. Okay, specific heat of water rather than specific heat of ice. But then you get up here until you get the water to 100 degrees Celsius, which is really hot. And when you get to 100 degrees Celsius, then it quits heating and starts changing phase. And that's what we call the boiling point, or the latent heat of vaporization, going forward or backward. Now, I didn't give you what those values were, okay? But the formula is exactly the same as before. Q is equal to M times L, but this time it's L sub V, okay? Now, finally, when you've got all the water boiled away, no more liquid water, now you can start heating up the steam. And this is what we call superheated steam. Steam at higher temperatures than 100 degrees Celsius. That's the steam you don't want to be around, because it will burn you like crazy. So if you have a steam leak somewhere, stay away from it. Now, my wife cooks sometimes in an Instapot. Those are really nice. It can cook a meal in a very short time. But it's sort of like the old pressure cookers, because you let the pressure increase, and therefore the water doesn't boil, and it gets hotter and hotter and hotter, and it cooks the food very, very rapidly. Of course, it will burn rapidly, too, if you don't have enough protection against that to go on. But when it's through cooking, you have to let the steam come down gently. Otherwise, you could hurt yourself with that hot steam. So here again, since it's changing temperature, your formula is just the same as before. Q is equal to M C delta T. The difference in these three MC delta T's is what's the C. The C for ice, now I'm going to do this, I'll do it down here. The C for ice is 0.500. Now the units are grams per, calories per gram degree Celsius. The C for water is 1.00 calories per gram degree Celsius. The C for steam is 0.48 calories per gram degree Celsius. That's the only difference in the three formulas. What value for C we have? C for ice is 0.5, C for water is 1, C for steam is 0.48. Water. Now that's heating or cooling. Okay. The latent heat of fusion, which is melting or freezing, that L sub F, the L sub F for water. Now this is water, nothing else, just water. Okay. This is on table 4.4 on page 104. The L sub F for water is 80. Look at that. Oops, wrong one. Here it is. 80.0 calories per gram. 80.0 calories per gram. Whereas a latent heat of fusion for water, you talk about a lot of heat, 540.0 calories per gram. Notice you don't have degrees Celsius because there's no change of temperature. So the latent heat of fusion for water is 80 calories per gram. Latent heat of vaporization for water, either heating or cooling, is 540 calories per gram. And then for some reason they always stick it in here, the mechanical equivalent of heat, which is a good thing to know. And I'll put this in here somewhere. I'm going to change my pen color. And they like to give it this way. I'm going to give it the way I like to do it. 1 calorie, little c calorie, is 4.184 joules. Okay? The way they like to give it is 1 kilocalorie is 4,184 joules. Well, why don't you just say, these numbers are closer together, 1 and 4, they're pretty close. Why put a K here and not have a K there? So this is the one I like to use, but you use it however you want. Okay, does that make sense? All right, now I sort of went past a couple of things here. Page 102 had those two latent heat formulas on it. They look just alike, it's just the values are different. There is a closer look on page 103, almost whole page there on passive solar designs, which is sort of stuck in a weird place here, but it's a really good read, okay? And I'll give you just a couple of things here, and I don't know if Dominique has noticed this or not, but it probably hasn't been so awfully cold since you've been in the class here, but those people who were in the first mini-term back in January and February, sitting by the windows there, they could get pretty chilly. It was mostly, I can't remember exactly who, but Seth sat over there both times. Well, the reason is that's just one pane of glass, okay? That one pane of glass is not a good insulator. It gets cold, it gets hot, okay? Now, more modern glass, if you go over to the new Academic Success Center, if they don't have double pane glass there, they should be shot, okay? Because they should surely have modern stuff. Double pane glass will keep you from losing nearly as much heat and out of the windows, okay? Now the other thing, those windows are so loose when the wind blows. That's why someone put a piece of paper in there. You see it in the corner there to keep it from rattling so much. They were complaining about the sound, but Really, the complaint is how leaky these windows are. Now, our old house, like I said, our house was built in the 1930s. It has single pane glass. But what we did, we put storm windows on the outside, so now it has a airspace in there that you don't have a lot of movement of air. Okay, you have some. It's not as good as double pane glass, but it's better than a single pane glass. Okay. What's that? 3:45. What time is it? No, see, I don't have my clock. What? It's what? 3:30. We got 15 minutes, so let's get as much done as we can. All right. So they talk about some passive solar designs, and I'll let you take a look at those. They talk about a Trumby wall, which I'd never heard of before I read the book. I've never seen one to this day except in this picture here. And it sort of does make sense. And then you can also do is a isolated solar gain design used to separate the structure and collect and store the solar energy, which is a good thing to do, especially in the wintertime. In the summertime, it's not any good here, but anyway. So I'll let you read that for your own. Let's go on and do example 4.7 at the top of page 104. Let's see if we can get this done before we run out of time. Okay, I'm going to erase that, and I think I'm still with my yellow pen, so let's do it. How much energy does a refrigerator remove from 100 grams of ice? So what's 100 grams? What's that a measure of? That's the mass, and it starts off being the mass of the ice. Okay, 100-gram mass of ice. Okay, from 100 grams of water. Oh, I'm sorry. I read it backwards. We're starting with water here, so sorry about that. I started with ice. Okay, so 100 grams of water at 20 degrees. 20.0 degrees Celsius, okay? To make ice, at minus 20 degrees Celsius. How much energy does the refrigerator remove from 100 grams of water at 20 degrees Celsius to make ice at, minus 10 degrees Celsius, okay? I misread my problem. Okay, there's the problem correctly. Okay, what's the first thing that refrigerator's got to do? Now, what is 20 degrees Celsius approximately? 20 degrees Celsius. Room temperature. That's 68 degrees Fahrenheit, which is pretty close to what we are in here, I bet. We may be 70, I don't know. They don't have a thermometer up there like they used to. So we're water at room temperature, 28 degrees Celsius. So what's the first thing that refrigerator's got to do? The water's at 20 degrees Celsius. You're trying to make, what you got to do? You got to what? Not heat it up, cool it down. You're trying to make ice. Remove the heat from it. Okay? So the first thing you got to do is remove the heat from the water at 20 degrees to get it down to what? Before you can make ice. 0 degrees. So what are you doing? You're changing the temperature of the water. And what's the formula for changing the temperature of the water? The question is, how much energy does it remove? So energy in this case is in form of heat. So Q is equal to, and what formula do we have when we're changing temperature? MC delta T. And the material is water, so we use the specific heat of water. So what mass do we have? What mass do we have? 100 grams. 100.0 grams times, what's the C for water? No, 1.00. What units? Calories per gram degree Celsius. And then what's our temperature change to get from room temperature water down to freezing water? What temperature change is that? What temperature does water freeze? 0 degrees Celsius, so you had to drop it 20 degrees, 20.0 degrees Celsius. Now when you look at this, the grams go out, the degrees Celsius go out, and that leaves you with calories, and that's 20 times 100 times 1. That would be 2,000. So the amount of heat removed to get the water from 20 degrees to 0 degrees, this is 2,000 calories. Okay, little c calorie. You could call it 2 kilocalories if you wanted to. That would be all right. Okay, so first thing you did, you cooled the water down to 0 degrees. Now what do you have to do? Cool the water to 0 degrees, but what do you have to do next? Anybody? Remember? What we've done now, we're going backwards on this thing. We cooled the water from 20 degrees Celsius to get it down to 0 degrees Celsius. That was our MC delta T. This one right here. Now what do we have to do? It says melting here, but we're going this way, so we're not melting, but if you're removing heat, you're freezing it. Okay, you're freezing it. So you do this one, your phase change. What's your formula for the phase change? Q is equal to M L sub, and since it's fusion, freezing, that's L sub F. So what's your M? 100.0 grams times, and the latent heat of fusion for water is, oh my goodness. Seth is here. Gotta find you. There you are. Okay. And by the way, congratulations are in order. Mr. King got one of the awards today. 2. Yeah, that's right. All right. Excellence in Art Award, and I think also Commercial Art, wasn't it? Huh? These are, oh yeah, okay. Okay. So, couple of, way to go. Congratulations. Did any of the rest of you? I don't recall. I didn't notice your names. They were going so fast and furious there for a while, I couldn't keep up with everybody. What's that? Oh, all right. Now, what was the latent heat of fusion for water? Anyone remember? 80.0 calories per gram. There is no change of temperature, so you don't have degrees Celsius in there. The grams go out, and that gives you 8,000 calories, or 8 kilocalories, little c calories. Okay? Now, one more thing you've got to do. Now you've got water down to, you cooled it from 20 to 0. That was a specific heat. Then you changed the phase with latent heat, and that took you from liquid water to solid water. But then once you got all that ice frozen, that water frozen to ice, you now have to drop it down to minus 10 degrees. That's hard to see there. Let me take the my visual aid out of there, which I needed, but ooh, yeah, no, that's not what I wanted. Okay. Oh, there we go. Now we need to get it down to minus 10 degrees. So you're going from 0 to minus 10. What are you doing then? What formula do you use? Q is equal to, anytime you have a change of temperature, you use which formula? MC delta T. You use specific heat. Okay, the mass is still 100 grams. It's now 100 grams of ice, not 100 grams of water, but it's still 100 grams. Your C for ice this time, what's the C for ice? .5 calories per gram degree Celsius. And then what change of temperature you have to go from 0 to minus 10? 10. Okay, you multiply that by 10.0 degrees Celsius. Okay, so 100 times 10 is 1,000, but times 0.5 or a half, that would be 500. And the grams go out, and degrees Celsius goes out, and that leaves you with 500 calories. Okay, so what did you have? 2,000 calories here, 8,000 calories there, 500 there, so it's a total of 10,500 calories. Which, if you do want to use a bigger unit, smaller numbers, that would be 10.5 kilocalories. Okay, that's how much energy you have to remove from 100 grams of water at 20 degrees to get that in ice at minus 10 degrees. Different formula, different constants for every step of the way. All right. And that's what they come up with too. They give you 10.50. Now, I don't know how they get 4 significant digits when the temperatures are at 3, the mass is at 4, yeah, I agreed there, but your specific heats are only at 3. I don't know how and latent heat only at 3. I don't know how they came up with justifying 4. It's 10.5. Or 10,500. Okay. Now, how are we doing on time? It's what? 3:40. Let's see if I can get let's get this slide done. Here are your phase changes, okay? And the things that we deal with, okay? Now, this is not changing temperature. This is only changing phase. If you're going from a solid to a liquid, then that's the latent heat, because you don't see the heat, you don't sense the heat. It changes your phase, not your temperature. That's the latent heat of fusion. Okay? If you're going from a liquid to a gas, then that's the latent heat of vaporization. You're vaporizing the liquid. If you're going from a solid to a gas, and that doesn't happen frequently, but it does happen, and that's called sublimation. The latent heat of sublimation. Okay. Now this is if you're heading in this direction. In other words, you're adding heat to the system. Then you're melting the solid to make a liquid. You're boiling the liquid to make a gas, or you're subliming the solid to make a gas. Okay? Now if you're dealing with water, the latent heat of fusion is 80 calories per gram of material. Latent heat of vaporization, 540 calories per gram. They didn't give us the sublimation. It's not really all that important. We don't run into it that frequently. Okay? The temperature for water is 0 degrees Celsius for your melting or freezing point, and 100 degrees Celsius for the boiling point. Sublimation depends on temperature, pressure, other things like that. So they don't get that. Now, if you're going the other direction, you're removing heat from the system, meaning you're starting with a gas. The first thing you do is, they use the same term, sublimation. If lack of a better term, I guess that's what you have to say, but that would be the latent heat of sublimation of water, whatever that happens to be. Then the condensation point starts happening at 100 degrees. You don't usually see it there, but it does. So that's the condensation point, and that's the latent heat of condensation is 540 calories per gram. Okay, and then when you're going that way, the latent heat of fusion is that's at the freezing point. degrees Celsius for water, and that's 80.0 grams, calories per gram. Okay. So how are we doing on time now?
2 minutes.
2 minutes. This is probably a good place to stop. Okay? So we will not finish the chapter today. Now, we are talking about 3:45, right? Okay, not 3:15. No, I want to make sure. Okay. So we'll pick up here next time. We don't have a lot further to go, just a few pages, so we'll do this Tuesday, which means we won't have the test on chapter 4 on Tuesday. The test for chapter 4 will be next Thursday. Okay? So what we depend on is whether we get enough covered in chapter 6 to have a lab next time. So that's the unknown here. I think we'll have time to cover it, but in case we don't, we may have to have a really long class on Tuesday. Hopefully we'll get far enough along to have the lab. Okay? And I think we're going to wind up just about right. So anyway, let's pause here. Okay, each one of the 3 teams has 4 cups of water, partial cups anyway, and they were measuring the temperature in cups 1 and 2. All 3 teams got them measured?
Yes.
Okay, then take the thermometer out of 1 cup and pour the water from that cup into the other cup.
Wait, what you said? What you said?
Okay, you got both temperatures? Okay, take the thermometer out of 1 cup and pour it into the water into the other cup and see what the temperature of the mix becomes.
Going down. They going down. Deflating.
Okay, when it comes to equilibrium, read what the temperature is of mix 1.
28. Mix 1 is 28. All right,
you ready? Then remove the other 2 cups and put your thermometers in those. That's cups 3 and 4 as you see them. Put the thermometers 1 in each. It doesn't matter where you put those, okay. All right, 1 in each. Okay. When they come to equilibrium, measure the temperatures of those 2 cups of water.
All right. Cup 3. 40.
Okay. As soon as you got it, get it.
Cup 4. It don't matter.
Okay. As soon as you get those 2 temperatures, stop.
11.
You said 11?
Yeah.
Okay. All right. Now, estimate what you think the next mixture is going to be. You saw what the first 2 temperatures were and what this mixture was. Now you estimate what you think the next mixture is going to be. Whatever you estimate. Y'all got the estimate done?
Hold on.
Okay. That's what I'm asking.
Yes.
Ain't no wrong
Okay, y'all got an estimate?
Yep.
Write it down. Just go. Yeah, it's a guess. Just make a guess. Okay. If you write down your guess, then pour the 2 together.
You're supposed to leave in there. This is good, right? You're supposed to leave it down here.
Wait. Yeah. Okay.
Put it back in there.
What you doing?
Okay.
It smells like gas in here.
Let's
It
be
smells like gas.
Okay. Into the trash.
All right, it cracked.
Okay, be careful, people. Okay.
What do we do?
The trash is over there. Okay, I meant to say that earlier. These cups with no water in them, they're unstable, so be careful with it and be gentle. You may not need the other.
Oh.
This is an expensive lab, you know? Okay. Now,
All right, 31. You was right.
Okay. Now, the question is, listen to the question carefully. Were the temperatures of cup 1 and 2 similar or dissimilar to cups 3 and 4?
Similar.
Very similar, right?
Mm-hmm.
Okay. Was the mix 1 very similar to mix 2? The actual, not your estimate, the actual. Why not?
Because there was more hot water.
Ha, very good. The amounts of water were different. You don't just average temperature. What you're doing is, okay, you're measuring temperature, but it depends on how much heat is there. And since there was more hot water in cup 3 than there was in cup 1, therefore you wound up with a warmer temperature there. Is that right? Yeah. Okay. So you answered number F then. Okay. Now, let me get the scales down for you.
All right.
Okay, we've got 3 things, but only 2 scales. So
I'll get one.
Okay, thank you for offering.
All right.
Okay, I'll put one here, but y'all share with these guys. Okay, get you an empty cup, or empty your waters from the other cups. Okay,
All of it?
all of it, and be careful with your thermometers, please. Okay, now.
All right, place a stop on cup on scale. Easy scale. 0 to scale.
Okay, you can empty that water, but take the thermometer out.
It's supposed to be in ounces.
What's that?
Ounces?
Ounces.
Ounces?
Oh. No. Grams. The scale's measuring grams.
You gotta pour water.
Wait. Don't get carried away. Let me carry you away.
That's the old fashioned one like this. I don't have no water to it. I don't have no water yet.
Then I went to place styrofoam cup on the scale.
Pour water to the cup until it's a little more than.
On there first.
What do you want to say?
This one I moved.
Okay.
This is good.
We did up. I don't have no water to it.
I don't say 6.3.
Right.
Drink your damn thing. Is it?
At work yesterday.
Okay.
I'm gonna say that's just kind of No, it's not right. It's of water. Hey, bro. You know what?
Yeah, you can dump all that water out.
His feet, so just the end of it.
Yeah. Dump all of them out, yeah.
Hang over the good cloth. Like this looks like this ain't right.
Okay. Okay. Have y'all zeroed the scale with your styrofoam cup on it, right?
Yes.
Okay, now I just, okay,
What's that say? Half? Well, that's so funny.
okay, what have you done?
I ain't do nothing.
Okay,
I ain't do
it's supposed to be an empty cup on the scale, zero the scale.
I ain't do this.
Okay, somebody did something.
I did.
Okay,
I ain't-
empty cup on the scale, zero the scale.
All right, it's 0, sir.
Okay, now you're supposed to have left the top on it, but it's okay. Pour that until it's maybe just a little over half full and stop. You can do the same thing. You zero the scale? Okay, then pour it just a little over half full, not much over half full.
Well, the cup's too.
Okay, carefully full. Okay, wait, just a little over half full.
Okay, well, that ain't even close.
Okay,
That's it.
okay,
We good, bro. That's all estimated.
okay. I would get a paper towel and get the water off the scale first. Okay, as soon as they're through and drying the scale, I can get it and do the same thing. You see what they, not what they
So,
did, but what
it's
they couldn't
340.
have done. Huh?
340.
Okay, record that.
All right.
And then put,
340 grams.
yes, that's what it
We
was.
doing math.
Okay?
What's
Okay. And then once you pour the water in, cover your
Wipe it down for me.
Okay.
I got it.
Get them off the scale once so they can use it, and you do the same thing. I'll be right back.
Okay, y'all do the same thing. Get the water. Alright. The temperature of the water is 45. Y'all be doing crazy. Y'all
Mass
both.
of water, 240 grams. Place your thermometer in the water and look at the temperature. What's that say?
Say 43. Everybody. 43 Celsius.
Place another solid on cup of scale.
What you eat?
Was it zero?
And what nigga say alcohol cup is?
It's not on something.
Did you put another cup on the scale?
That's it. That's it. 4 zero.
That's close enough.
Okay. Zero the scale with that, and zero the scale with that, and zero the scale with that. Okay.
Zero.
Okay. Now take a few cubes of ice.
How many
I would
got
say
two?
not more than 50 grams. Okay. Not less than 50 grams. Keep adding until you're a little more than 50 grams.
Bless
Okay.
you.
Y'all got the temperature of your water, right?
Welcome.
Yes.
Okay. Huh?
Is there supposed to be water in it?
No, 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 no.
Oh, the same
Your other one,
cup.
yeah.
Bingo, we done.
Wait. Wait, what are you doing?
I'm sorry.
You got the ice.
No, wait.
This is the same cup.
The same cup. You already measured the
Yes.
mass. Did you measure the temperature?
Yes.
Okay, then you're supposed to put the empty cup on there, zero the scale again.
That's what
I know, but you then put it in there.
So 50 grams.
Okay? Empty cup on there, zero the scale. Empty cup, yeah.
Hey,
Place the ice into the water and first place the ice into
Okay.
the water.
Zero.
first.
That don't make
Now
sense.
put ice in it until you get up to 50 grams or higher. Or
Place
whatever
the
50.
ice into
Okay,
the water
now you got it.
first. Cook.
Record the mass of the ice. Have you done that? Well, whatever. Record it. Have you done it? Take it off.
I need ice.
Okay? And now put the ice into here. Okay? Did y'all understand that?
This is
Okay.
grammatically
Put an empty
incorrect.
cup on the scale.
Okay.
Sure it's
And
empty.
invert
Zero the
second
scale.
cup
Hey,
And then put enough ice to get a little bit more than 50 grams.
when the ice was completely. Then we're not.
What we got?
hold on. 35, everybody.
Ain't no 35.
Wow.
It's a check periodically to determine when the ice is complete. Then measure the temperature of the water. So you're gonna have to wait until the water.
Does anyone have a cell phone with a thermometer that you can measure?
I got a question. What kind of phone is that?
I don't know. I'm just asking if you do.
It's an Android.
I don't know.
You don't? I don't know either. They used to have a thermometer here, and they've taken it out. And now I don't have. Oh,
Ain't
wait.
that about a bit?
One of these thermometers will do. Okay. Never mind.
It goes good.
So there's an app that works.
I'll use one of these thermometers.
Movie.
You wait till the ice melts.
Oh.
Just
What's
Which is
better?
the ice that I say.
Ice
chill.
down? Yeah.
Ice
Hell yeah, man, that quick.
Okay.
The ice, they stole it.
How much is it now?
Okay.
That's our
While y'all are waiting for your ice to melt,
We don't
Are
have
you?
no ice.
We done. We done.
okay, well then, are y'all, for those waiting for the ice to melt or not, come over here. We're going to go to the third part.
Wow.
Huh?
What's the equation?
We're going to get to that in a minute. Okay? Okay. Okay. Come here to the table. There's two thermometers there. They should be about the same. They've been sitting on the table all day. Read the thermometer off. Don't hold on to the end. You'll make the temperature go up. Okay? That's why I said leave them on the
That's the heat
table
loss.
and read them. Yeah.
25.
Okay. Is that the one on the table too?
125.
Don't touch the ball.
22.
Okay, 22. I use that because you touch the ball, it'll be on.
Alright.
Okay, wait. Everybody, come to this table.
That's the heat loss.
Come. No. We're doing the part 4 induction now. Okay. Well, y'all are waiting for the ice to melt, right?
Yeah.
Okay. Come here. Measure the temperature on the table without touching the ball. Okay.
23.
Degrees Celsius. Okay? Everybody got it?
What?
Measure the temperature on the table there. This is conduction, number 4 on page 2. Estimate, okay.
23.
Read the temperature. You don't need to write it down anywhere. It's just, okay.
So that's the
Read what it
temperature
is.
of the room.
22, 23 degrees. What did I hear?
23.
23 degrees. Okay. What would you say the temperatures of these pieces of metal or plastic are? Not touching them. They're on the table right next to the thermometers. What would you say their temperatures are?
The metal's probably the same.
Wait. They're on the table. Same place.
They the same.
That has to be the same. Right?
But you said that.
Okay, good.
Okay.
It would be 23 degrees or 22, whatever you
Hey,
say,
it's
right?
23, y'all.
Everything's 23.
Okay.
Okay.
Now, lift one each, okay, and place it on the facial cheek, and tell me which one feels.
Cheek.
Okay.
Gonna break me out.
See which one feels good.
And see which one feels warmer.
Take one for the team.
Okay, no, everybody.
The plastic feels warmer.
Plastic.
Yeah.
Does the plastic feel
It
warmer?
feels warmer. Everybody do it, so you don't have to.
Hell no.
Okay, well, I'm depending on you. I'm doing this. My face gonna break out.
The plastic's cold. The plastic's warmer.
It feels warmer.
Yep.
But we know they're at the same temperature.
That's don't crazy. Which
Okay?
feels warmer?
Why is that?
Because of what you said earlier
Okay, and what was that?
about the metal being an absorber or something, so it tries to spread it all out through the metal. Basically,
Not absorbent.
conductor.
The metal is a good conductor, so what's happening, your face is right around 66 degrees, 65 degrees Fahrenheit. I mean Celsius.
Okay.
Okay? 65 degrees Fahrenheit. Celsius, I keep saying it wrong. Whereas, and both of these are at 23 degrees.
Okay.
You touch this, what you feel here is the 23.
Mhm.
What you feel here, this is not a good conductor, so it's rapidly coming up to your 65. So that's why it feels warmer. They're at the same temperature. This is just not conducting your facial heat away. This one is, big time.
So the metal has higher.
Conductivity.
Okay.
Okay. Now
Alright, class.
go back and check and see if your ice has melted yet. Okay, let's measure the temperature of the iced water.
We already did that.
Okay, that's D.
Gang.
Right?
Yeah, we have temperature of iced water.
Yeah, did you get that?
Yes.
Okay, good deal. All right, everybody got the temperature of your iced water?
Yeah.
Yes or no?
Yeah.
Did y'all get it? Did y'all? Okay, now. You ready? Number E. Write the equation to determine the heat loss of the original water. The original water was, okay? Yeah, we are still recording. Original water was the one that was on A and B. Okay? A and B, you have the mass of the water and the temperature of the water. Right? Now that original water did not change its mass. You added ice to it, but that was a different mass. The original water had the same mass as it did before, but it has a new temperature at the end, right? Okay? So what you want to do is measure the, first, what is the equation to determine the heat gain by the melting, E. to write the equation to determine the heat loss of the original water, and then you're going to determine the heat loss. What's the equation when you have a change of temperature?
Q equals MC delta T.
Absolutely. Q is equal to MC delta T. I'll write it on the board here if I've got a pen that works.
What's a delta sign?
Change.
Okay.
Wait. It's a triangle.
Oh,
Okay.
MC
Q
delta T.
is equal to MC delta T. Okay? Now this is the heat loss by the original water. Because it did get cooler, didn't it? I hope. Yay or nay?
Yes.
All right, good deal. Now, what was the mass of that original water? As in A. What's the mass of the original water?
3.
Whatever your group was, it should be in grams. And it was around what?
340.
340 or something around there. Reasonably close. Grams. What is your C? Anyone know that?
Is that heat?
Is what heat? Has a name.
Celsius.
Huh? Okay. Q is going to be in calories. This has calorie in it, but it's calorie per something else.
Gram.
Absolutely. And what is that? That has calories per gram degree Celsius. What is that unit called? I think you're trying to say it.
I'm trying, but I don't remember. Is it C?
It's C. That's what it is. It's specific heat. Specific heat.
C don't.
What is the specific heat of water? What is the specific heat of water? 1.00 calories per gram degree Celsius. Okay, so whatever your mass was, you're multiplying that by C, which is 1.00 calories per gram degree Celsius. Okay? Now that original water started at temperature B and wound up at temperature D.
So it's 32.
I'm sorry, I don't know what you were
The
saying.
mix.
The mix too.
Huh?
So you did B minus D, which gives you the change in temperature.
Yes, change in temperature.
So it's good.
Okay? And that will be whatever your experiment showed.
And then you
Okay.
multiply them all together.
Then you multiply those three together, and you notice your grams here from your mass will cancel out that gram. The change in temperature here will cancel out the degrees Celsius, and you'll wind up with calories.
I'm lost.
Okay, where?
At the triangle.
Okay,
What's the
delta
temperature
T.
supposed to be?
You started off your water at what temperature?
Start off a
No, calorimetry.
5,100.
Calorimetry. Calorimetry. That calorimetry. That's down here. What did it start off? No, that's grams.
The B minus
43
D?
degrees Celsius. What was your end temperature? Next page.
Sound right. Was it D minus B or
Okay, the difference of that is your delta T.
B minus
Delta means
minus
difference.
D?
so we divide it.
No, baby.
Here we go.
Difference. What is
Difference is subtraction. So
Is it supposed to be a negative number?
no? Use the larger number minus the smaller number.
So it's 4.
That's what you do.
It's 15.
You said B minus.
okay, so then you do 15 and then you multiply all of those together.
345.
Multiply your mass of that original water, A. Are y'all paying attention at all?
Yeah.
Okay, mass of the original water, A, times 1, which is not going to change the light of the number in it, and then times your change of temperature. And that will the grams cancel grams, delta C, degree Celsius cancel degree Celsius. That'll give you so many calories. Did y'all get an answer yet? Did y'all get one?
No.
I got it.
Good.
So,
There's 1,000.
oh, that's his name, right?
That was.
Flowers.
C, which is
Wow.
what?
He said, wow.
Okay.
Multiplied by 8. That's the difference.
That's the
That's the
difference.
delta.
We had
B minus D.
46. Oh, 46 is 30.
Yeah.
So, no, not 8. 6.
What? 51,000.
Oh.
What kind of number you got?
51,000.
That's
I mean,
45,000.
5100.
I mean, 5100.
Now, are y'all all measuring the same thing?
That's why I said
Our
something
rate
right.
is different than everybody.
Cause she said B minus D.
It's B.
Is it B minus D in the
This
first section or the second?
B,
I think it's the same.
this B, 43 minus this B, 28.
I know what we're doing. It's B.
This
Wait,
B
wait.
minus
That's
this
MC
B.
and Delta.
All right. Okay. Now what's it?
Wait. Delta
So
T,
it won't be
that
15, but it
change
should be
difference.
around the number.
That's why you
Oh,
took the
that's gonna be
difference between
No,
the two temperatures.
You can negative 4.
Because this B 43 and the other 50.
no, you said
Oh, let's see.
43 minus 28.
Okay.
You can leave that problem.
Okay, hang on.
Okay, so it's still 15? Okay, so multiply all those together. Okay. No, that's right. It's 5,100 calories.
Y'all got exactly the same?
But we have different measurements. It's just hers was 48 minus 1. So I don't know. There's different measurements, but it got the same number, 15.
Wow. Okay.
That's crazy.
I know it.
Crazy.
Okay. Now, you had a mass of ice, number C, right? So number F, let's read F first. Write the equation to determine the heat gained by the melting the ice. Okay? Nothing else. Okay, this is F. Okay? Write the equation to determine the heat gained by the melting ice, and then we'll calculate that. So what's the formula you use there to do the heat gained by the melting ice? Second? What formula is that?
Is it ML something?
What is it right here?
That's heat loss. That's heat loss.
Oh, that's my favorite ice though.
Yeah.
Let me see. The hole in the middle.
That's number E.
Yeah, that's what I said. What is
Heat loss.
what's that?
Okay? What's the formula for the heat gained by the melting ice? Anybody?
Is it ML something?
MLB?
L. Did anything evaporate here?
No.
It was heat of fusion. Okay? MLV. MLF. You got me saying that. M times L sub F. L sub F is one entity. It's just indicating it's fusion rather than vaporization. What was your mass of the ice? That you get from number C, from letter C, right?
Yes.
Now, is there a temperature change involved with the melting of the ice? No. It just melted the ice. So and what was the latent heat of fusion for ice? Or for water? Latent heat of fusion for water.
Was it not?
What?
Was it not 0? No.
What?
Was it 0?
I hope not. Okay.
Zero?
It doesn't need any heat to melt. Okay. What is it? No, it's not one. That's the specific heat of water. The latent heat of water. Now, some of you weren't in class, the rest of you were. Okay? What's the latent heat of water? I mean, the latent heat of fusion for water. Anybody? You bring them up.
Let me look that up. Hold on. 1.3?
Huh?
1.3?
I don't think so. Where'd you get that? That is the rate of conduction. It's the latent is further back. No, you're right. You're going in the right direction. That's specific heat. That's too far to go the other way. Oh, right. And a little bit further. Right there. Yeah. Latent heat of fusion for water. 80.0 units. M here. So you have the mass, whatever the mass was in C, and you multiply that by 8. And that's the heat gained by melting the ice.
4,640.
What's that?
4,640.
Sounds reasonable.
I got it.
Y'all got it?
Yes.
You got it? Okay. But you got
5,040.
pretty high. Okay. Now, and that's calories, right?
Yes.
All right. Now,
4,000.
number G. Okay, what you've done now, let's get an idea of it. You just melted the ice. What temperature was the ice when you started? Assume zero. Okay? It wasn't fresh out of the thing, so it's probably right close to zero. Okay? You melted the ice. That didn't change the temperature, right? And then what you do is warm the ice, warm that melted ice, which is water now, until you get to D. So it went from 0 to D. Right? You got the temperature at D?
Yes.
Okay? So your equation was what? Since you haven't changed the temperature, which equation do you use? The first one. Only this is now a heat gain. QG by the warming of the water. Okay? And this would be M. Now that M is your ice. M. Okay? You melted it. And it's,
Ice water?
okay.
It's the ice.
Second.
The ice water.
It's the mass of the ice. You melted it here, so now it's water.
Oh,
Okay? But now it's that same mass times C times delta T. You have a different delta T here. Did we lose
MC delta T.
MC delta T, right?
Yes.
Okay?
Okay.
But this mass is the mass of the ice, because that's the one. See, this is the mass of the original water. This is the mass of the ice, and this is the mass of that ice once it melted, so it's water again. And it's C, same C as you use up here, but it's a different delta T, because now you're going from 0, when it was ice, up to your final temperature. Right?
So you're going from 0 to what it was once the ice had melted.
Yeah.
Okay.
Is Austin coming back, or you know what's going on? I'm sorry? Okay. What I just said. Now, it really is helpful if you put units down. Okay, so go back to the first thing. Okay. These should be degrees Celsius. Okay. Except I can't believe that's 11. No, you had your cups backwards. Yeah, but it's okay. But cup 1 was the warmer cup, cup 2 was the colder cup. Okay. Yeah. What's that? Yeah, your heat gain was greater. Okay? And the question is why?
The heat. Because there was larger amounts of water.
No, that doesn't have really anything to do with that. I don't know. Okay. Okay. I don't understand what you got here. Okay. M is what?
Why you did it?
Why? You didn't have any ice?
Yeah, I did.
Well, then why'd you put 0?
I don't know the temperature of the ice.
Okay. If you were why you use the latent heat of fusion. So now it's melted and become water. You didn't gain any or lose any. You still have the same mass, and that's the mass you put here. That's
So
why I
80 is mass.
The mass is 50.
don't know what the mass is.
The mass is.
Yeah, I said aim for 50. Did you get it right at 50? I mean, not 51, 52.
So it wouldn't take much to go from room temperature to
Okay. Then that's your mass times C, which is 1, times the change of temperature of that ice when it warms up. After it melted, it warms up to the final temperature.
the ice from the regular.
So it's going from higher to lower
Lower
temperature.
the height to
Okay, I still see a lot with no units. I don't know what you're talking about.
like the ice.
What's the mass of the ice?
It would still be like at first
63
like,
what?
level-
Oh, I got
so like
1400.
the next, but since ice is like
Grams,
it's
of
got
course.
more of a jump.
Okay.
But it's not, but
Now,
you
so
got
what's
it
the
going while there was a higher
heat
heat
loss?
gain. So I feel like that would explain
No.
why it's a higher loss.
Mass is grams, heat is not
That would
grams.
make more
So
sense
it's
for
mass.
heat loss. We need to know why the heat gain was higher than the heat loss.
What were your units here? Mass is grams, C was
Okay. Well,
on the board. No, it wasn't
that
on the board.
actually makes sense.
C was,
Because
that's the number. What's the units? Look on the board.
Actually, it should be.
it should be that.
Calories per gram degree Celsius. But you had grams here,
Yeah.
so that counts as about the grams.
But don't-
And you had
we'll go
change
in
of
the
temperature
ice
was
change.
degrees Celsius, so that is, so this is calories.
Then ice water.
Okay, what you got?
That might be because going from ice to water, it don't
That's
change,
adding.
but
Okay,
water to ice.
all right.
it does.
Now, which is
Some-
larger?
Something to do with that.
Okay, again, okay. Okay, which is larger? The heat gain or the heat loss?
The heat gain.
By how much?
1,004.
What?
300.
300.
300.
300 what?
Okay.
Second, calories. 300 calories, that's the difference here. Okay?
300 cow. Cali.
What? Okay. Did you do this one? Right. Okay. Multiply.
They're gonna get colder.
Okay. I'll add these two together. Total heat gain. Okay.
Why? I don't understand why.
Okay, we're gonna get to that. I'm trying to let him catch up to where y'all were. Okay? This is lab partner lab.
Okay.
Temperature.
Okay.
Temperature of the room. It ain't cold.
That makes sense.
And even if it was cold, it ain't that cold.
Do that later.
Water cold, heat loss.
So you got this. Now, which of these is larger? This
But
one?
the heat gain was
That
greater.
one? Okay, by how much?
No.
These are calories. You didn't put the
Yeah.
units in.
And then the heat loss is 5100 and the heat gain is 5400.
Okay. Now, okay. Now, what did you get with larger?
Oh wait, no. That's right. The heat gain feels
Alright, we don't watch.
Okay. What was your answer?
Yeah, that's right.
3 cow. Calories.
The whole the total
300
heat gain.
calories.
Yes. And a larger
Was
gain.
the heat gain?
Yes.
Okay, y'all agree?
Yes.
What did y'all have?
For which one?
That's the heat gain.
Quite a bit, but it was a heat gain, right?
Mhm.
And
But it's the
they
total
have
heat
finished it.
gain. Cause I guess you gain heat twice.
Just heat gain.
Me too.
Which is larger?
So that's what I said, cause we temperature.
We've been brainstorming.
No, which is larger? Heat
I
gain
said
or
it's
heat
something
loss?
about the temperature of the room.
That's what I said, cause it's not cold there.
Heat gain, okay.
It can only be higher.
Yeah.
Sounds good.
Okay. Now,
which was more hot.
Now,
That's what I said. You said that. Was
I cannot answer the question of why now because all of you had
Just brush it off.
Okay, wait. Final temperatures of something that was higher than room temperature, right? So room temperature.
he said 20 degrees Celsius.
What's that?
He said the table was
20 degrees Celsius, pretty close to it.
Yeah, and ours
Okay.
were higher.
So it seems like to me you should have all wound up with a net heat loss. Okay? And you got what you got. So I can't answer the why for you. Most of the time I can because you had, if the temperature had wound up, the final temperature had wound up cooler than room temperature, then you probably gained heat from the room. Okay? You wound up with a room temperature higher, the cup temperature higher than the room temperature, which to me would have indicated a heat loss. Now here's what I'm guessing happened, is that you took your final temperature measurement before all your ice had melted.
No, all
Oh,
right.
yeah.
Definitely have just not put enough ice.
No, you measured how much ice
We
you
probably
had.
some more mad.
I think it was the ice.
I think it was the ice. It was good.
It was totally melted?
Yeah.
Yes.
Okay. So I can't answer why then. Because all of you wound up with a higher heat gain than you had a higher heat gain, right?
Yes.
But you had a higher temperature than room temperature.
Mm-hmm.
So,
So did the temperature of the water just been too?
all that worked out, you started with the temperature of water. If you'd have had, now the only other thing would have been, that would have still been a heat loss. Okay, I can't answer why. Experimental error is the only thing I can say.
They say DNA.
Say again?
So you know, it's
Yeah, that's not.
So what's the
You got an
answer?
answer,
We didn't hear
but I
that.
can't
Yeah, I
tell
feel
you
like
why
we
you
do.
got that answer.
So what?
Experimental error.
Well,
That's what I said. Okay.
that doesn't make any sense.
Well,
So
some,
what he
some,
said makes sense.
Yeah,
Could've got to that.
but how we did this, I guess.
Well, we wait like 10 minutes for the milk, so it should be ice.
well, then you should have been losing temperature to the room while waiting for that. Okay, and you were gaining. You said you wound up with a heat gain,
Yeah.
and I don't know how to accommodate that. And just about every other thing. Occasionally it comes out. But let's look at it on the other hand.
I think he said maybe it should.
Okay, let's look on the other hand.
Styrofoam cup, that's why.
No, the styrofoam cups were pretty decent insulators. Here's the other thing. Let's take your difference there. This is just, we'll make a guess here. Take your difference
Okay.
and divide it by, and which did you say was larger, the heat gain?
Yes.
Divide it by your heat gain,
By total heat gain?
by the total heat gain.
0.20.
Okay. You're 20%. What were you?
0.94.
Hey, right.
Can't possibly be.
I'm right.
Did y'all do total heat
300
gain minus heat
Divided
loss?
by that.
And got 300?
Yeah.
Our heat loss was 5100 and our heat gain, our total heat gain was 5400.
Okay. So I think I can sort of, what did yours come out to be?
18.
Let me see that.
So 5400 divided by.
Wait, no.
You doing the total heat gain?
No, 300 divided by the heat gain, the larger number.
Divided by 5400.
5400.
What are you doing?
No. Literally.
300
divided by 5400.
400.
What you got? You
Point
got,
zero
you got
five.
less than 6%. So yours was close enough. That's a very good approximation. So you could have been plus or minus anything. Not bad. Yours was like 20%. So I think part of that was ice into the water and out of the water and stuff. I think that was part of yours. What did yours turn out to be? What's that? Oh, man, that is really, no, oh, that's 27%. I thought you, okay. That, I can't account for that much, okay? So it's experimental error. I don't know where the error occurred. Y'all were doing things, well, I couldn't see what you were doing. I think you were rushing things. That's probably where the error came, okay? So I can't account for anything else. Most of the time, I usually can. But yours is close enough that it's usually close enough. That was just bad error. And it may be your tolerance of your thermometer or anything. On the scale.
Okay.
All right, good deal. Now, remember on Tuesday, we will finish chapter 4 and we'll get started in chapter 6. We don't do 5. And the odds are then, hopefully we get far enough in 5, 6 that we can do the first lab in 6. Okay?
Almost done with lab.
What's that? Okay, please.
We almost done
This
with
is
lab.
not our stuff. Okay? So let's not mess with it. This is biology stuff and some of it may be sensitive. So don't mess with it. Okay, good deal. Thank you. Thank you. All right. I'm going to end the recording. Now, there's